course titled The Growth and Collapse of Orogens and the Exhumation of Deep Seated Rocks in the Himalayas, being held here at the Center of Advanced Studies in Chemistry, Punjab University, Chandigarh, from November 24th to November 28th, 2025. This course, organized under the Global Initiative of Academic Networks, GIAN, brings together global and local expertise to explore next generation therapeutic strategies. Before we begin the workshop, I would like to request all of you to please rise up for Punjab University anthem. Thank you, everyone. Please be seated. Now, to begin with the felicitations, I would like to invite Professor Yojana Rawat, DUI Ma'am, Punjab University, to extend a warm welcome to our foreign faculty, Professor Rodolfo Carosi, University of Torino, Italy, in appreciation of his gracious presence and contribution to GIAN. I now request Professor Gurjasprit Singh, coordinator of GIAN program, to warmly welcome Professor Yojana Rawat, DUI Punjab University, Chandigarh, by presenting her with a bouquet of flowers. I would also like to request Dr. Mahesh Thakur, course coordinator, to extend a heartfelt welcome to Professor Minakshi Goyal, Director RDC Punjab University. As we begin this auspicious event, let us invoke the blessings of knowledge and wisdom. The lighting of lamp symbolizes the dispelling of darkness and the ushering in of enlightenment and knowledge. I would like to request our esteemed guest to join us in lighting the ceremonial lamp. Let the light guide us towards a path of innovation and discovery. To formally inaugurate this workshop, I would now like to invite Professor Gurjaspreet Singh, Department of Chemistry, Punjab University, and local coordinator of GIAN, to deliver the welcome address.
A very good morning to our respected Chief Guest, Professor Yojana Rawat, Dean of University Instruction, Punjab University, Professor Minakshi Goyal, Director of Research and Development Cell, Punjab University, Professor Gangaram Chaudhary, Chairperson and RUSA Coordinator, Punjab Chandigarh, our distinguished speaker, Professor Rodolfo Carosi, University of Torino, Italy, Course Coordinator, Dr. Mahesh Thakur, Department of Geology, Punjab University, Chandigarh, faculty members, all participants, and everyone present here. I extend a heartfelt welcome to all of you to the international workshop on the growth and collapse of origins and exhumation of deep-seated rocks in the Himalaya, organized under the global initiative of Academic Network GIAN. Professor Karosi is a leading structural geologist specializing in continental tectonics and orogenic belt evaluation. His work combines structural analysis, geochronology, and numerical modeling to study deformation processes such as shear zones, faults, and tectonic metamorphisms. With over 150 peer-reviewed publications and several geological maps, he has made substantial contribution to understanding crucial scale tectonics. We are truly honored to have you with us today, Professor Karasi, and we look forward to gaining valuable insight from your talks. The global initiative of Academic Network GIAN in higher education was launched in 2015. It is a flagship program of Ministry of Education, Government of India, designed to tap into the global talent pool of scientists, innovators, and entrepreneurs, and to foster their engagement with the Indian Institution of Higher Education. GIAN aimed to catalyze excellence in higher education institutions across the country. It is a dynamic program that promotes participation of international faculty as visiting professor or professor of practice, offering specialized 5 or 10-day course to enhance academic collaboration and knowledge exchange. The first GIAN course at Punjab University was conducted in 2016. Till date, 30 courses have successfully organized, and we look forward to conducting many more in the future. Punjab University has submitted 40 new proposals under Phase 5 for the upcoming financial year 2026-27. I wish you all an enriching and insightful learning experience with Professor Carson. Thank you.
Thank you, sir, for your kind words and for setting the stage for what promises to be a highly insightful workshop. We are deeply honored to have Professor Yojna Rawat, DUI Punjab University, today to deliver the presidential remark and grace the occasion.
A very good morning to everyone. Uh, I welcome you, sir, particularly on this very occasion. It is a matter of pleasure and honor for me to be here at the inaugural of this GIAN course on the growth and collapse of origins and exhumation of deep-seated rocks in Himalayas. This program reflects the growing emphasis on Himalayan studies and geoscientific research in India. The Himalayas, one of the world's youngest and most dynamic mountains belt, continue to evolve under active tectonics with the increasing frequency of natural disasters such as landslides, flash floods, and earthquakes. Exacerbated by climate changes and unplanned development, the need for deeper scientific understanding has never been so greater. These hazards do not only threaten lives and infrastructure in the Himalayan region, but also impose enormous social and economic burden on the communities. Understanding the growth of collapse of origins as well as the exhumation of deep-seated rocks, it is fundamental that the geological processes that shape our mountains. Courses like this enable students and researchers to build the advanced skilled necessary to address challenges in natural hazards, assessments, sustainable development, and disaster mitigation. I extend my heartful welcome to Professor Rodolfo Morosi from the University of Tornio, Italy, whose participation exemplifies the true spirit of international academic collaboration. His expertise and engagement will undoubtedly enrich this program and inspire young geoscientists in India. Well, I'm not the expert of this subject, and we for that we have Professor Rodolfo with us from Italy, who has worked, for decades, I'm sure, in this domain, and he will definitely enrich your knowledge in this domain. But what my personal experiences with the Himalaya is also very much a matter of concern for me personally, because as a young student, right from the college days, I've been going on mountaineering camps and trekking and advanced hiking, trekking and skiing expedition. And almost 15 years, I would go for trekking twice a year in the month of June and again in the month of September or October. And I've been very fortunate that I was born in that era when we had nature called nature and seasons were seasoned to be natural in their natural, shape or natural pattern. And I remember, going to Kolhai Glacier, Lola Valley, and Pangi Valley in Himachal, Mani Mahesh twice. I went to Rohtang Pass. On foot, went from Kullu, Manali, almost 150 students to Rohtang Pass. And then Amarnath Cave, And all these places, they remind me those years when these things would not happen. Rarely any such incident would happen. But now, when monsoon comes, we all are scared, frightened, and you all know what happened this year in Uttarkashi. The kind of videos we saw, they were so disastrous and so horrifying, and hundreds of people they lost their lives. And secondly, I'm a very, very passionate driver, and I love to drive in the mountains only, not in the plains, because the kind of traffic we have. And it used to be really fun, and like I was very passionate about driving, especially to Shimla side and to Kullu Valley. And like when you go little higher in the mountains, you see these meadows, you see the shepherds, see the flock of sheep, but now, if you go to Shimla, you don't really feel any kind of adventure in driving or experience nature because there's no forest left. There is construction all over. There are restaurants, dhabas, and resorts everywhere. Earlier, there used to be patches almost 20 kilometers or 30 kilometers. You wouldn't see any construction, and you knew this is the this is the patch where you really you are going to enjoy the nature, going to see forest. If you go from Kullu to Rotang, you don't see any forest. There are few trees left, or some jungles left because they are not reachable. They can't be cut. The trees are so big, and they have been left. And rest, everything has converted into construction, which is very sad and very horrifying. And we all know these are also the major reasons of the topic that we are discussing today. The pattern of climate has changed across the globe, and there are so many reasons for that. Growing population, particularly in our country, the kind of population we have, the kind of pollution we have, and the kind of unmindful growthness, land mafia, and so many things are happening around us, and there's no control over these things. And the kind of exhumation is taking place across the Himalayan region is very, very worrisome. So it is very saddening for me personally, because as I told you, I belong to Garhwal, Uttarakhand. I belong to the mountains, sir, which is a part of Himalaya. And fortunately, I went to my village last year, and my village, they have nice roads now. But of course, there is internet. But it is the same village that I saw 30 years back. This we still have, flock of sheep and goats and cows and buffaloes, and there's only one or two tiny shops where you find normal things. But otherwise, most villagers, they grow their own vegetables, their own fruits. So it feels good that still there are some belts of Himalayas where people, the villagers especially, who love their land and who love their profession as being peasants or agriculture, they're still saving this culture. But otherwise, if you go to Punjab, you don't see anything. It's so bad, like I remember I was driving to Punjab with one of my friend from France, and suddenly he told me, say, oh, I feel like shooting something. I said, what happened? He said, I can't imagine a McDonald right in the fields of, wheat or something. So, like we to say we are saying we are having a lot of growth around, we are having development, but we really have to really pay attention and be really mindful what this growth means and what are the hazards of this kind of growth. And Himalayan range, which is a new range of mountains, which is not a very old or ancient range, and it is under great threat. So for that, this GIAN program, this particular series of lecture has been designed. I'm very much appreciative of Dr. Gurujaspreet Singh's efforts, and I'm happy. And I like to share with you, this is my first, program that I'm here invited to not participate, because I'll be leaving soon, but to be part of it. And at least this makes me realize that what is happening in our university, how we are trying to make our students acquainted with latest, problems or latest issues relating to their field, their domain. And I truly appreciate this platform. I think this is one of the most vibrant platform of Punjab University as per research and development goes. And I congratulate you, sir, and your entire team. Dr. Chaudhary is here, and Dr. Meenakshi Goyal, who's a director, research and development cell, and whose unwavering support make these things realize. And my esteemed colleagues, some of them are sitting here, and you all students. My only request to you is, you have a research scholar, a person, a scholar who has come all the way from Italy, thousands miles from here, from a beautiful land. So try to be attentive and alert and curious, and interact with him, ask him questions, and try to understand what he's trying to talk to you. And imagine he's going to talk to you about the Himalayan region. He's not from India, but he's going to talk to you about this region because he has studied this very subject, and he's here with the knowledge that he has gained over the years, the experience and the expertise he has. So I think it's a very good opportunity for you to take the maximum benefit of this event. So with these words, I wish you all the best, and thank you very much, sir, for inviting me here. I'm grateful to you, and you give me opportunity to meet the scholars also, and to address the students. Thank you. All the best.
Thank you, ma'am, for your valuable insights and for always supporting academic endeavors like this one. We are privileged to have Professor Minakshi Goyal with us to deliver the inaugural address and grace the occasion with her words.
Respected Dean, University Instructions, Professor Yojana Rawat, Um, Distinguished guest of honor, Professor Rodolfo Corossi, Professor Gangaram Chaudhary, Professor Gurjaspreet, Dr. Manish Thakur, faculty members, eminent scientists, inverted experts, course coordinators, and dear participant. A very good morning to all of you. It is my privilege to address this gathering on the occasion of the inauguration of the GIAN course on the growth and collapse of orogens and the exhumation of deep seated rocks in the Himalayas. I extend my heartfelt congratulations to the organizing team for conceptualizing a program of such academic depth and contemporary relevance. At Punjab University, we firmly believe that research must transcend theoretical boundaries and contribute meaningfully to societal advancement. The Himalayan region, dynamic, fragile, and scientifically fascinating, stands at the heart of India's geological heritage and national priorities. Its active tectonics, complex structure architecture, and increasing susceptibility to natural hazards make it imperative for researchers to understand the processes shaping this monumental orogenic belt. The study of mountain building mechanisms, organocollapse, and the exhumation of deep seated rocks is not only a scientific endeavor but an essential step towards hydrological disruptions and sustainable development across Himalayan terrains. The insights gained here have profound implications for disaster mitigation, infrastructure planning, climate resilience, and long term environmental stewardship. The GIAN course exemplifies the interdisciplinary approach needed for such complex investigations. The integration of structural geology, petrology, geochronology, geomorphology, climate science, and advanced geospatial technologies offers participants a holistic perspective on lithospheric processes. It is the blend of theory, analytical techniques, and field based understanding that enables true scientific advancement. We are honored to welcome Professor Rodolfo Corossi from the University of Torino, Italy, an internationally respected authority in structural geology and tectonics. His outstanding contributions to the understanding of modern and ancient orogenic systems have significantly shaped global perspectives on Himalayan tectonics. His presence here, though through the global initiative of academic networks, enriches this program and reinforces Punjab University's commitment to fostering strong international collaborations. I would also like to recognize the dedicated efforts of Professor Gurjaspreet Singh, Dr. Manish Thakur, Professor Jia Chaudhary, and the organizing team for bringing this academically rigorous and forward thinking program to fruition. Their vision reflects the spirit of innovation and scholarly excellence that Punjab University strives to uphold. To the participants, I would like to emphasize that this workshop is not merely an academic exercise, it is an opportunity to question, to explore, and to contribute to one of the most significant scientific challenges of our time. You belong to a generation equipped with advanced tools, computational techniques, and global knowledge ecosystems. I encourage you to use this platform to cultivate curiosity, embrace interdisciplinary thinking, and develop the scientific rigor necessary to propel Himalayan research to new heights. I sincerely hope that this workshop leads to new insights, enduring collaborations, and a renewed commitment towards impactful and responsible research. I wish the program a great success and look forward to the intellectual outcomes it will inspire. Thank you.
Thank you so much, ma'am, for your valuable words. To conclude this inaugural session, I now invite Dr. Mahesh Thakur, Department of Geology, Punjab University, to provide insights about the theme of workshop and also deliver the vote of thanks.
Good morning, ladies and gentlemen. On behalf of the organizing committee and Punjab University, I express my deepest heartfelt gratitude to have Professor Yojana Rawat, Dean University Instructions, Punjab University. We are profoundly grateful for your encouragement and for gracing this event with your valuable presence and presidential address. Our sincere thanks to Director Research and Development, Professor Minakshi Goyal, for motivating words and for guiding us towards the strengthening research driven initiatives at the university. We extend our profound appreciation to our distinguished guest of honor, Professor Rodolfo Carsoi, Professor in Structural Geology and Tectonics at the University of Torino, Italy. Sir, your deep expertise in tectonics of orogenic belts, particularly your extensive structural and microstructural studies in Himalayan belt, makes you a globally recognized authority on very theme of our workshop. Uh, Professor Karsoi has published more than 150 international peer-reviewed publications, and Professor Karsoi has supervised numerous PhD and MSc theses, and served as a chair of IUGC Commission on Structural Geology and Tectonics, president of Italian Geological Society 2024-2026, chair of ICN IUGC Italian Commission 2023-2026, and he was also head of the Department of Earth Sciences 2018 to 2021, and he is actually director of School of Natural Sciences at the University of Torino. He is a editor and co-editor of several journals, including Lithosphere, Geosciences, Journal of Virtual Explorer. Uh, so in this workshop, we have around 40 participants, which include students from various states like Himachal Pradesh, Punjab, Haryana, Maharashtra, and some of the students are also joining online, who are not able to come. So, so I also thank Professor Gangaram Chaudhary, Department of Chemistry, and a very special thank also goes to Professor Ghosh Jaspreet, local GIAN coordinator, for meticulously planning and dedicated efforts in making this important workshop a reality. A special thanks to the chairperson, Department of Geology, Punjab University, for her support and for her encouragement. Finally, my heartfelt thanks to all the faculty members, students, researchers, and participants. Your enthusiastic presence and commitment to learning truly define the success of this inaugural function. With these words, we formally conclude today's session. We look forward to an academically enriching journey in the days ahead from November 24 to November 28, 2025. Thank you.
Thank you, sir, for your heartfelt words of gratitude. We extend our sincere thanks to all our dignitaries, speakers, and participants for gracing the inaugural ceremony with their presence. With that, ladies and gentlemen, we now conclude our inaugural session. Let's take a short break for refreshments. Please join us for high tea and return by 11 as we begin the first lecture of this workshop.
in 1993, I attended a field trip from Kathmandu to Lhasa, and I worked in the Tibetan side of the Himalayas, and I was fascinated by the landscape, by the geology, and by the people living in the Himalayas. So after that, I worked many, many, many times. I attended many field trips in the Himalayas, and I worked a lot in this very nice continent. So I am very happy to be here, and I will show you some research result, some topics about the Himalayas and the other origin in Western Europe, because I worked also in the Alps, in the Apennines, in the Variscan belt of Europe, and the old Orogen, the Paleozoic Orogen, and also in the Transantarctic Mountain. I was in Antarctica 6 times to work in the Transantarctic Mountain to make geological map and tectonic studies. So I will show you some result of this long experience because I'm quite old. And I hope that this course will be useful to you to understand a little bit better the orgenesis, the Himalayan origin, and some topics of structural geology. So if you have a question, please ask me. No problem. You can interrupt every time when you need. So I hope this this course will be useful. Okay. So as a reference book, I suggest you these two books to go into depth structural geology. The first one is structural geology from Akun Fossen. It's a very nice and modern book. There are also a lot of resources on the web, e-modules, e-charts, movies from the book, so you can enjoy a lot using this book. And this one, Microtectonics, is by Pacher and Trau. The second edition is not 2025, 2005, not 25. But it is very useful for the microstructure because it is the best book dealing with this topic. Okay. So if you need, I have a PDF copy of this one, of the macrotectonics. I can share with you. Okay, in the first day, I will give an introduction to orogens and orogeny, a little bit recall the Wilson cycle, classification of orogen, and the architecture of an orogen. Are you from bachelor, master courses? Master studies. So you have a little bit knowledge of, okay, thanks. Because it is not easy to explain to a public without knowing. Okay. So an origin is a region of the Earth crust that has been deformed and uplifted through compressional tectonic processes, leading to the formation of a mountain belt. As you know, the Himalaya you have just here, you know very well what is. Uh, it typically includes folded and faulted rocks, metamorphic zones, igneous intrusion formed during an orogenic event, mountain building episode. We will speak about the Himalayan origin, of course, the Alpine origin. There is 1 hour devoted to the tectonics of the Himalayan origin, and also the Variscan origin, that is the Paleozoic mountain popping out in Western Europe, and also, of course, in Italy. Okay, orogeny is a set of processes and phenomena that led to the formation of a mountain range. This satellite view of the Himalayas on the right. You can see the Mount Everest group. Sorry. Vabbè, non ci sta. Okay, and there is a distinction in literature in between orogeny and tectogenesis, because one is referred to the uplift of the mountains, and the other terms is referred to the overall processes, but now with orogeny, we include all the processes leading to the formation and uplift of the mountain. So in the book, in the literature, you can find this differentiation, but orogeny is the best term to use. Okay, a mountain range is due to crustal shortening in tectonic convergence zone between plates and are the result of both thermal and mechanical disturbance of the lithosphere. Not only the forces are important, but also the temperature. This doesn't work. The thermal perturbation is very important in making up an orogen. We have also the deformation and metamorphism of lithospheric rocks. We'll deal mainly with metamorphism and ductile deformation of rocks in this course, as well erosion and sedimentation. Erosion is very important, and also sedimentation. And also, an orogen can form an important climatic barrier, such as the Himalayas, that was built up after collision 55 million years ago, and it was a very big climatic barrier. And in the Himalayas, there was the first study by Jamieson and Beaumont, two Canadian geologists, that coupled the tectonic and climatic processes. In the maybe in 2000, 2001, the first paper. They made a very nice numerical model of the orogen, including the erosion. Erosion was a very important factor helping tectonics to go on. Goes on. Hmm. Okay. Okay. We deal with the collision, so we must recall Tuzo Wilson. He's a Canadian geologist that was the main developer of the Wilson cycle, but the Wilson cycle was named after this work by Kevin Burke in 1975. So, and Tuzo Wilson was famous for plate tectonics, also for the discovery of hotspot transform fault, and the Wilson cycle that is very important tectonic processes that will lead to the end to the formation of an orogen. At the beginning, you have a rift of the lithosphere, and the continent started to split by extensional tectonics. So you have a lot of normal fault in the thinned part of the orogen. After a lot of time, the continent are completely broken and separated, and the new oceanic crust started to develop in between. Then you have seafloor spreading, and after movement of plate tectonics, you can start subduction on one side of the two continents. Subduction means the, the oceanic crust go in subduction below the continent. You can have a accretionary prism and some other things. After the total consumption of oceanic crust, you can have collision. So the two far continents come in contact one with the other, and with the formation of the continental crust. And during this process, you have erosion and sometimes the thinning of the crust, and the process start again. So there is a complete cycle that needs maybe 250 million years to complete. Mhm. And during the history of the Earth, there were several of these cycles leading to the formation of supercontinents, the big continents, the Pangea, Rodinia, and in the future, there are some tectonic geologists that are working with the GPS velocity of the continents, and in the next 250 million years, we'll have the Pangea Ultima, a big supercontinent in the future, very far in the future. Okay, the process is very similar. In this paper, more recent by Wilson, but not the same Wilson, another one, of course. There is another picture uh, speaking of the Wilson cycle, but more or less the significance is the same. Okay. There is one difference at the beginning because you can see here not important subduction of the continental crust because during the development of plate tectonics, people believed that the continental crust cannot go in subduction because it is too light. Mm? The density is too small to go inside. But in the 80s, 1984, the French mineralogist Christian Chopin, found coesite inside garnet in continental crust in the Alps, close to Turin, close to my town. And coesite means that the rocks underwent subduction up to 100 kilometers in the lithosphere. So after the 80s or the 90s, people believe that also continental crust can go in deep subduction. Okay. And in the same massif, the Dora Maira massif that we will speak about in the next lessons, we the people are finding a lot of coesite in oceanic unit, oceanic derived unit, in continental derived units, and in the last few months we found also fossils in ultra high pressure rocks. We found polynomorphs, pollen, and acritarchs of Silurian and Permian age inside the very high metamorphic rocks. So it was a very nice discovery just published 1 month ago in scientific reports by my research group. Okay, so if we give a look to the convergent stage, bringing leading to the formation of the of a of an orogen, you have the continent A, continent B. The continent A is affected by a passive margin, so a lot of extension. Now they are very common to find hyper-extended margins with a lot of piece of the continents above the oceanic crust and the mantle lithosphere assumed by exhumation. You have the subduction of the oceanic lithosphere, the formation of a continental volcanic arc by the fusion of the continental oceanic crust, accretionary prism due to the convergence in between the continent B and the oceanic lithosphere. After that, you have the formation of the suture, because all the oceanic lithosphere is consumed by subduction. Sometimes oceanic lithosphere is transported above the continent by abduction. So you can have pieces of lithosphere not deformed or metamorphosed just above the continental crust. And at this stage, the continent collide, come into contact. In the Himalayas, the age of collision is around 55, 60 million years. There is discussion about this, but the most accepted age is this one. After collision, the, the game is not over. You can have the thickening. The lithosphere is thickened. There is erosion because the mountain belt is growing. So erosion is very active. And also exhumation of the metamorphic rocks, because the deep-seated metamorphic rocks are brought to the surface during the collision or after the collision. In this stage, you can have also deformation towards the foreland. You can have two foreland, two fold and thrust belt on both sides of the orogen, or on one side. It depends on the characteristics of the lithosphere. In the Himalayan orogen, you have only a foreign basin in the south to the Indian side, but not to the Tibetan side. Okay, so this continent is very strong for the Himalayan side. In this nice picture movie, we can see the movement of India towards the north, the collision, and the hyper collision of the indentation tectonics proposed by Molnar in the 70s. And in this stage, India continued to push into Asia, and you have a lot of deformation in the continental crust, and also you can have a big transcurrent fault, strike slip fault, such as the Altintag fault, and so on. You can see again, it's simple, but it is very nice. Subduction of the oceanic lithosphere, collision, and the formation of the main thrust of the Himalayan belt. The main central thrust, main boundary thrust, main frontal thrust that you know very well because you live in this. Okay. About climatic and tectonic processes up to 1000, people don't believe that erosion was important in building up the Orogen, but after this paper, there was most important by Beaumont and others 2001. They proposed a channel flow model that we will speak about in the next lessons. And this channel flow model deal with molten rocks below Tibet flowing to the south, and this process is allowed by the monsoon erosion because the monsoon is active since 25 or 30 million years. So in this long time, the amount of erosion is comparable to the amount of convergence and tectonic velocities. So it is very important process to develop tectonics. Okay, and this is the first paper that pointed out to this aspect. So erosion is very important. Now it is not the fundamental factor, but erosion could help tectonic to proceed. Okay, in this picture you can see the Himalayan from satellite. You can see Mount Everest here to the south and the very dry region of Tibet. So you have a lot of erosion of the southern flank of the belt. Erosion, putting away some sediments, the most part goes in the Bengal fan. Okay, this is dry Tibet, and this is Nepal, who is green aspect. Okay, the erosion at the mountain front is very different because you can see the rainfall millimeter for years from India, Nepal, and Bhutan. In Bhutan, you reach more or less 5 meters and if it is of rain in 1 year. Is a picture of one expedition in Bhutan where we had a lot of rain during the day and the night for 20 days. So very few work, few sample collection, and we had to do it under the rain. Okay. Just to remember the geometry of the mountain building, you have the internal zone of hinterland where metamorphic rocks are present. Much metamorphism happened in this rock. You have a fold and thrust belt moving the belt towards the foreign basin. You have the foreign basin filled by sediments coming from the eroded mountains and the continental interior with no deformation. It's just to remember the main characteristics. Okay, if we give a look to the world, this is a nice picture, not so precise, but just to have an idea what happened of what we have in the world. In orange, we have the shield, the platforms in violet, orogens in green blue, this one. We have the active orogens or all the orogens, the basins in this color, large igneous province in this color, such as lycanthropes that you know very well, and the extended crust in yellow. So just to have an idea of what happens at the world scale. Mm. In the same picture, similar picture, you can see the different periods of activity of orogen. Starting from the Archean, you can see in the South America, North America, on Australia, Siberia, China, the most ancient crust, early Proterozoic, middle Proterozoic, late Proterozoic in violet, Paleozoic in blue, more or less, and the Meso and Cenozoic in yellow. So you can see different ages of formation of orogens all over the world, just to have a broad idea. This is not so precise because the Variscan orogen, the Paleozoic orogen, is lacking in this part of Europe, but just to have an idea of what happens in the world. Okay, we'll speak about the Himalayan belt that you know. In Europe, with the relief map, you can see the Alps, the chain of the Alps. Turin is just here. Mm. The Apennines, and this part is made by Paleozoic rocks, the Variscan orogen, cropping out in all this part, this island, and also in some part of the Alps and the Apennines. Mm. So just to have an idea of the geography. Okay. I put some names because they're not so familiar. Yeah. Okay. The orogen can be classified as a linear orogen, such as the Urals, in between Europe and Asia. Is the green belt formed during the lower Paleozoic. There is only curvature in the northern part of the polar Urals, and these are very long and very linear. Is 500 kilometers, so you can see the very long development of this orogen. There are some orogen, such as the Variscan orogen in Europe, that is made by a curved shape. You can see more or less the main attitude of the tectonic contacts of the fault in the Ibero-Armorican arc. Ibero means Spain. Armorican is this place of the French nation, and there is this curvature and another one in the east, and this part is affected by the very huge shear zone that we will deal in the next lessons. Okay. Apart from the shape, there is another formal classification of origin by Hank Zwart in the 70s, because he divided alpine type origin, such as the Himalaya and the Alps, and the Hercynian type, or Variscan type, based on the structural, metamorphic, and magmatic characteristics. But Hercynian or Variscan type orogen, the Paleozoic one, are characterized by a large volume of granitoids and regional high temperature metamorphism and poorly developed fold and thrust belt. Okay. In the alpine type orogen, we have metamorphism, it is high pressure or ultra high pressure metamorphism, few granitoids, and a well-developed fold and thrust belt. But this difference are not real. because it depends on the history of the belts. So at the end, after the development of plate tectonics, we recognize that the origin are made by the same processes. So it depends on the amount of thermal energy and the tectonics involved in the processes. You have the same history. Okay, so there is not a big difference characterized by this. So a much more modern classification of the origin is made by the one proposed by Beaumont and the others in 2006. That is similar by the classification of the star in the Hertzsprung-Russell diagram. You have here the temperature and here the luminosity. And for the origin, you can have here the temperature, more or less the same. And instead of luminosity, you have a magnitude of the origin. So the amount of lithosphere involved in the process. And the classification has two end members. You have a large hot origin in this part of the diagram, and here the mold called origin. And for example, you have a main sequence, such as the star. So a small called origin can evolve towards a large hot origin, and you can see some kind of origin. The Southern Alps in New Zealand is a classical, very small called origin. The Alps are here. The Greenvillian in the Canada is here. The Variscan is this side, and the Himalayan Tibet is the most classical example of large hot origin, because you have a large lithosphere involved in the process and a large amount of granites, and the high temperature is testified also by partial melt crust. You have a lot of migmatites inside the origin involved. Okay, this is more or less the same sequence. So you can have also a trend like this, and you can deviate from the orogenic main sequence towards another kind of sequence, like the one followed the Variscan origin. Okay. So the processes are the same. It depends on the temperature, on the amount of temperature, and the amount of lithosphere involved. But the tectonic processes are more or less the same. Okay, so according to most of the author, Himalayan Tibet is a classical large hot origin. The crust is 60-80 kilometers thick. There is a central elevated plateau, the Tibetan plateau, nearly 5 kilometers, flanked by wedges and foreland basins. There is a mechanically strong upper crust, superstructure, very weak infrastructure. Ductile flow of the weak infrastructure is in response to pressure gradient. So these are the main feature, and you can see a picture from the Tibetan side to the Mount Everest from the base camp in Tibet, and this from the Tibetan side, just Mount Everest and maybe Choyu. So you can see the snow level at the 6,000 meters. Okay. Another classification of the origin is made by Carlo Doglioni. Do you know the symmetric art classification? Or Carlo Doglioni is a professor at University of Rome La Sapienza. This one just a few days ago during the conference, and he proposed that the Earth is asymmetric, because you can have some very steep subduction and very shallow subduction, and it depends if the subduction is towards the west or towards the east, because there is a flow of the asthenosphere from west to east. If you have a subduction that is opposite to the flow, the subduction is very steep, and the chain above has some characteristics. If the subduction is in the direction of the flow, the mountain belt above is of alpine type with different characteristics with respect to the Penninic types. This is below, so west dipping subduction and east northeast dipping subduction are very different and give rise to different characteristics. The continent move according to equator, a tectonic equator that is not the geographic one, but shows a sinusoidal shape. So the continent flow this direction. So in the Himalayas, you have a northeast dipping subduction, a subduction of the Indian plate below Asia, and this flow of the asthenosphere to the east is caused by difference in density between the lithosphere and the mantle, because lithosphere is less dense than the mantles, and during the rotation of the Earth, lithosphere move in this direction. So the velocity is less than the velocity of the mantle. So you have this movement, and then there is a flow of the asthenosphere to the west. The main cause of this flow. And according to Doglioni, the mountain belt are asymmetric because if you have a west dipping subduction uh, in opposite direction to the flow of the asthenosphere, you have an origin that is smaller with respect to the origin that build up above subduction in the direction of the flow, the asthenosphere. So more or less, he studied the Alps. It is this kind of belt, and the Apennines, this kind of belt, and he expanded this study to all over the world. You can see here more or less the main feature of the Alps here, the Apennines. You can see here the steep subduction below the Apennines with the volcanic Alps, the Eolian Islands, and a very deep earthquake up to 500, 6,600 meters below the Ionian Sea, whereas the Alps go in this direction in a very shallow angle with respect to the African crust, just to have an idea. Okay, so the two different type are this one. Apennine to the right and the Alps to the left. Okay, the main feature are these. The change is double in the Alp. You have a divergence towards the plane and towards the European side. The angle of subduction is one angle of subduction in the Apennine. So you have one single divergence that is towards the east in the Apennines, towards the Adriatic Sea. The topography is high in the Alps. You have several mountains reaching 4,000, 4,500 meters. And whereas in the Apennines is very low, the maximum altitude is 2,000 meters or 2,500 and so on. You have no back-arc basin in the Alps and well-developed back-arc basin in the Apennines. The foredeep basin, you have two shallow basin with low subsidence in the Alps, and in the Apennines, one deep basin with rapid subsidence. About metamorphism, the basement is deeply involved in the alpine orogen with large volumes of exposed high pressure, low temperature metamorphic rocks. In the Apennines, the basement is less involved, small volumes of exposed high pressure, low temperature rock. Okay. The magmatism related subduction show less volume of the alpine chain and much more voluminous in the Apennines. So you can extend this classification all over the world. And so the difference that Hank Zwart found in the 60s were caused by these different subduction direction. So there are some difference, but not in the processes, but in the subduction direction. Okay. You can see here also the actual altitude of the Apennines and the estimated amount of sediments of rocks eroded up to 3,000 meters. 2,000 meters. In the Alps, you have much more developed topography and much more amount of rocks eroded in the Alps. Okay. From Carminati and Doglioni, Earth Science Review. There are many, many papers about these topics. Okay, so you can see here the Pennines with the Becar here. It is the Iranian Sea, whereas in the Alps there is no Becar basin. Okay. Yes, they're more or less the same things, but I left some more picture on the right in the slides. So when you have a PDF, you can read the. Okay, the Europe. Okay, this is a picture, and this is a aerial view of the Europe. Mm. And in the simplified geological map, you can see Cenozoic alpine belt. That means the Apennines, the Alps, uh, Denariad, Orogen, and so on. In orange, you can see the rocks deformed in the Variscan belt during the late Paleozoic, the lower Carboniferous. And you can see that the most part of these rocks are not affected by later orogen, whereas in the Alps and the Apennines, you have pieces of orange rocks inside. That means that these all the rocks are involved again in new orogens. So it makes a little bit complicated the reconstruction inside this belt. In the northern part of Europe, you can see also the Caledonian orogen developed during the lower Paleozoic. So you have a lot of deformation, and of course, the study of the Alpine belt and Apennine is quite easy, not very easy, but possible. Whereas the study of the Variscan belt is much more tricky because several pieces are displaced, reworked in later orogens. Also for Corsica and Sardinia, Corsica and Sardinia was connected to French Spain to 25 million years, then they rotated during the Apennine orogen. So the Calabrian arc, this side, was put in this position, then migrated away towards the southeast during the opening of the Ionian Sea and the Bekarka Basin in the Apennines. So the construction in the Variscan belt is a little bit tricky. Okay, we will speak about mainly of the Variscan orogen in Sardinia and Corsica Islands. that are beautiful island in the Mediterranean Sea, and they are not affected by later orogens. So you can see the structure as they formed in the late Paleozoic. Okay, about about the ocean crust involved in the Variscan Belt, there are several hypotheses, or one oceanic crust, two oceanic crust, three, four, five, because up to the 18, 19, also 2000 years, some people found alignment of ecolgite rocks, and when they found a large amount of ecolgite, they put an ocean. So in the literature, there are several oceans separating the Variscan small pieces of the continent involved in the Variscan belt. Up to now, after this paper by Faure Ferrier 2022 in Geosciences, uh, the suture and the oceanic crust involved is only in three places. Le Conquête suture in this part, the Eovariscan suture here, and the Tepla suture here. So there are the three recognized suture zone with involvement of three small or big oceans, separating fragments of continents involved in the collision of for the formation of the Variscan belt. You can see here Corsica and Sardinia that are now in this position, but at the Paleozoic they were in this position, close to France, and also the pieces of the Variscan rocks in the Alps that are now deformed in a curved way, they were aligned in this position, just to have an idea. Okay, this is the same concept. In violet Paleozoic rocks affected by Variscan orogen. And you can see here Variscan orogen involved in the alpine orogen. If you remember a few slides ago, Belloni stated that much more basement is involved in alpine type subduction and less basement is involved in the Apennines. There are only few pieces in Tuscany and so on. So just to have an idea, this Pyrenean orogeny, that is the formation in this side. Okay. But for example, if you go in Spain, Massif Central, in Brittany, you can see the rocks as they were deformed at the end of the Carboniferous. And just to have an idea of the continent during the early Paleozoic, you can see Gondwana to the south, this ocean called the Lake Ocean, the Armorica Barrandia continental crust from the Armorican in France, the Lake Ocean that was quite big, the Avalonia continent. Then you have the Japetus Ocean with two arms, a Tornquist, the Japetus continent, separating the Laurentia to the west and Baltica to the east. So the Caledonian origin was formed by the collision of Baltica and Laurentia. The North Japetus was closed with the suture, and you can find this origin in Norway, Sweden, Denmark, in the northern part of Italy. This happened in the lower Paleozoic. After that, Gondwana started to move to the north, and Laurentia and Baltica, called Laurussia, started to move to the south, and you had the closure of the this ocean, the Rake Ocean, and the Take Ocean. So you have more or less two suture in this zone, leading to the formation of the Pangea at the end of the Paleozoic. Okay. Have you some question about this overall picture? Yes. Yes, there's a stripe-shaped continent. It's not so big, but very long. Mm, okay. Okay. And this part is ended. Mm. We can okay, 10 minutes before we can start the second part. Okay. Mhm. Mm, okay. Sorry. Mm. All the cold, all the hot. Yeah. Yes. Yeah, usually all the halogens are hot, but also the Himalayan Tibet origin is very hot. Yeah, because we have a lot of migmatites below Tibet, where seismic profile showing the hot melt below Tibet. So the amount of you have also a lot of migmatite cropping out in the Greater Himalayan sequence with a lot of leucogranites of Miocene age. So very, yeah, welcome. So now we will give some information about the deformation of the rocks. We're going to a little bit into depth of this kind of feature. We will speak about briefly of elastic deformation, elastic brittle deformation, fracturing, granular flow, cataclastic flow, with example for natural faults and fault rocks, friction and its control on rock strength in the brittle upper crust, and rock deformation experiments. But just a brief information. After that, we will start to speak about shear zone in the crust on the lithosphere and the kinematic indicators with some practical exercise in the afternoon. The books are the same, of course. Okay, you can see in these two pictures two different kind of deformation of the rocks. This is the San Andreas fault. This is a brittle fault cross-cutting the lithosphere, as you know very well, generating earthquakes. Mm. And on the left, you can see a folded calcite vein in the northern Apennines. So this a classical ductile deformation or ductile structure. You can deform the rocks without fracturing, and this is a deformation by fracturing, losing cohesion of the rock. So this deformation are due to the application of forces to rocks, and usually a small amount of deformation is due to elastic deformation that is recoverable. You can deform a little bit. If you do not apply the force, the rocks come back to the original position with no permanent deformation. But this is a small amount of deformation in the rocks. In structural geology, it is very important the stress, that is the force divided the area, because the deformation, it is not the same if you apply 1 kilos to 1 centimeter square or 1 meter square. So the amount of force is is important, but the area on which it is applied, it is causes deformation or not. So deformation usually involve a change in the position of the rocks, movement of the whole body, a change in the shape. You can see this scene section with oolitic limestone. When I apply deformation, there is a change of position, but also a change of the shape. From circular object, they become elliptical. This is a very clear example of change in shape. Sometimes you can have a change in the volume of the rocks. For example, when the sediments uh, became rocks, you decrease in density, you have the expulsion of water, and so on. So usually you have a decrease in volume of this, of the sediments becoming rocks. Okay. The classical example of elastic deformation is the rubber. When stretched, it returns to its original shape once the force is removed. And each rocks have its own elastic limit. Mm. After that, you can have a permanent deformation that could be brittle or ductile. But the behavior of the rock depends of the elastic limit. That it depends on the temperature and on the pressure that controls the mechanical behavior of the rock. And usually in a stable continental crust, you have the pressure that increases with depth at a rate of 33 megapascal for kilometers due to the lithostatic load of the rock, mm, the weight of the rocks. The temperature increases normally with a rate of 25 centigrade Celsius centigrade for kilometers, and the temperature promotes plastic deformation of the rock. Of course, if you are in a subduction zone, the gradient is much different, maybe 18, 15 degrees per kilometers. If you are in a geothermal area, such as in Tuscany, you have the mantle just 3 kilometers below the surface, so the gradient could be 50 kilometers per kilometer. So I refer to a stable continent with no much deformation. So if we give a look to the rocks in a vertical crust, you can see different behavior deformation due to the increase of pressure and temperature going down, of course. Other factors that affect the deformation of rocks are the presence of fluids. The fluids are very important for metamorphism, for metamorphic growth, and metamorphic change of minerals. And the fluids also favors brittle deformation. If you have high pressure fluids, you can break the rocks even they are in the depth. Mm. And also the deformation rate is very important because low deformation favors ductile behavior, so folding and shearing of the rocks, whereas very short deformation favors the fracturing of the rocks. You can see this example in the pack of Antarctica. Pack is the seawater, uh, the ice made by seawater. You can see here a glacier flowing from the higher part of the Antarctica towards the sea. You can see the flow lines and the folds because the flow is a few meters a day. And in this case, the pack that is thick 2 meters is broken by the strong wind flowing from the higher part of the um, of the continent, the katabatic wind that reaches 200 or 300 kilometers per hour, the velocity, and in this way very fast deformation broke the ice into pieces. The same is the rocks. Slow deformation favors ductile deformation. Very fast deformation allows the fracturing of the rocks. Okay. In this classical experiment that reported in the book by Twiss and Moore in 1992, a piece of marble, marble is made by limestone recrystallized the static growth of minerals. This marble is subject to deformation under different pressure, 0.1 megapascal, 3.5 megapascal, 35 megapascal, 100 megapascal. And you can see in this case there is a longitudinal splitting, the sigma 1, the main stress in this direction, and the pressure parallel to the sigma 1, increasing the pressure. It means going a little bit down in the crust. You can see a single oblique fracture, and at at, at 35 megapascal, you can see the transition in between brittle and ductile. You can observe something like fracture, conjugate fracture, but also the shape of the rocks change. It is a little bit compressed in vertical and extended in horizontal. Whereas at 100 megapascal, the deformation is completely ductile. So the body change the shape, is shortened in vertical and lengthened in horizontal with no fracture inside. So, okay, with you can see the different, this uniaxial deformation, triaxial depends on the condition of the experiment, but okay, just you can see in this picture by Fossen, in the book of Fossen, you can see sigma 1 with one fracture, sigma 1 and sigma 3, the confining pressure uh, develop one single fracture. The brittle ductile transition is one of brittle deformation, but a little bit wider, and the changing in the body due to sigma 1 and sigma 3, and the completely ductile deformation. In this diagram, there's a strain, elongation, and the stress. There is an elastic portion of deformation. After that, after the elastic limit, the rock underwent rupture and fracture. The same here. You can see the different shape of the red curves. The elastic, brittle deformation, elastic, brittle ductile deformation, and elastic and plastic deformation. So different. We will come back here in this graph later. Okay. This is a nice picture by Fossen. You can see a fault cross-cutting of the lithosphere with morphological expression at the surface. You can see the fault here. The first 10 kilometers, you have fault with cataclysmic rocks, incohesive fault rocks in the first kilometers, and the cohesive fault rocks towards the depth. At 10, 15 kilometers, there is a transition between brittle and plastic deformation because I remember you that the temperature and pressure are increasing. So, but of course, the transition is not sharp, but in a stable crust, it occupies nearly 5 kilometers. So the behavior in brittle and ductile, the transition happens in these 5 kilometers. Below 15 kilometers, you have ductile deformation. So the fault became a shear zone. The deformation is wider and wider, going into depth. And in this case, deformation is is happening during metamorphism because you have green-schist facies, amphibolite, granulite, colgate facies going to depth. So deformation and metamorphism go together, mm, are not separated. Okay, this is a picture from Ray and Matawar, where you can see the same deformation but in a contractional setting with folds and foliations. In the upper part, the deformation is brittle, the crust is brittle, and then you have a fracture and folds. You are in the upper structural level, so you are in this part. You can have also some folds, but they are passive folds or folds linked to thrust or to the geometry of the folds. In the transition zone, there is the brittle ductile transition. So you can start to form folds with a foliation of axial plane foliation in folds. Below 15 kilometers, there is completely plastic deformation. You have pervasive deformation, pervasive foliation. So the foliation is dominant in all the rocks deformed. You have folds, ductile shear zone, and also recumbent fold, tectonic transposition. So the original stratigraphy of the rocks is almost completely concealed or transposed by tectonic processes. Uh, Pervasive surfaces, defoliation, and polyphase deformation is very common. And you have ductile shear zone with mylonites, the fault rocks. And at the end, when you reach 650, 70, 700 degrees, you can have also the formation of pegmatites because you are close to the boundary of melting of the crustal rocks. Uh, okay. Okay, come back to elastic deformation. This classical example of elastic deformation, as probably you know, is a spring. You apply a force to a spring, the spring changing length. After releasing the force, the spring return in the initial state, so deformation is completely recoverable. In the rocks, this is nearly 1% of deformation, no more. 1% is this kind of elastic deformation. You know that the relation between the stress and strain is E, the Young modulus, just to remember. The relation between deformation, strain, and stress is linear. Classical example, very, very easy. In this graph, you can see uh, linear elastic during extension or contraction is the same symmetric situation. And just to have an idea, the Young elasticity modules in a gigapascal for quartzite, gneiss, granite, limestone. We can see that quartzite is a more uh, strong rock in respect to gneiss, basalt, granite. The shale of quartz coal are the less strong rock. Okay. This is very nice example because you have a rubber band in equal state. You can load by, by this quartz the material changing length, and after that the elastic limit is overcome, and there is a fracture just here, but the fracture is confined in this position. The rest of the body maintain the original structure with no damage or faults or fractures. Okay. Coming back to the crust, the brittle deformation in this part of the rock is made by fracturing or frictional sliding. Uh, the brittle flow that is in the lower part of the brittle field is made of a granular flow that is frictional sliding or rolling of fragments, and the cataclastic flow that is made by grain fracturing. This means that you have a flow made by a rotational movement of grains with no fractures, but the cataclastic flow is made by fracturing of grain, and they develop a flow in a brittle condition. We are just in this part. In this picture, you can see a brittle rock deformed. So these are cataclysite, this intact rock, and these are cataclysite made by fragments of the regional rocks. And here you have a cataclastic flow made by the fracture of grains moving in this part, allowing the deformation along this fault. Is an outcrop of Norway Caledonian origin. Okay, just the same things. Okay, in the brittle regime, there is the formation is governed by the Bayerly law. Someone of you remember the Bayerly law? This never. Oh, it is a linear correlation stress and strain in the first maybe 10 kilometers of the crust. So means that the deformation is the same in all kind of the rocks, independently of the if it is a quartzite or granite, but the slope of the line is 0.85 maybe, means that the relation is the same. So in all the rocks of the brittle part, you can follow a line like this, more or less. Not a good exposition, but explanation. But it is very, very common. Okay. Okay, so when you have a rock and the faults, you have the flow. So no, in the brittle ductile portion, on the ductile portion of the crust, the force with the rock made the flow. The flow means deformation that could be by faults or by shear zone, ductile portion. Okay, and the rheology is the study of the flow and deformation of all form of the metal. And during the flow, the deformation is controlled by the viscosity of the material. So we are going down, and the plastic deformation, the classical model is blocked on the surface. You apply force, you have to overcome the attritus in the surface, then the block starts to move. So this is in the graph, you have velocity of deformation and the stress applied. Nothing happens, you increase the stress, you apply the force. Nothing happens until you reach the yield stress. After that, you overcome the attritus of the surface, and the block starts to move at the constant velocity. And this is the perfect plastic deformation. Plastic means deformation of rock, not molten rock. Okay, this very ideal deformation, perfect plastic, and it could explain some kind of deformation of the rocks. The viscous deformation is the other way of deformation, but is much more applied to fluids. such as migmatites, for example, are useful for plastic deformation. You have a piston with oil inside, with separation. You applied the force, but the linear viscous deformation in this graph by velocity of deformation and the stress applied, the relation is linear with no yield stress like plastic deformation. But when you start to apply the force, uh, the movement the piston start to move in a linear way. And this deformation and also the plastic deformation are not recoverable. So the permanent deformation. So you can start to deform the rock and the deformation maintain its deformation. The fold are forever. Okay. And the viscosity with this strain symbol named eta by Greek alphabet describes the way in which fluids flow. So this the tangent of this angle eta is the viscosity of the material, and of course different materials have different viscosity. This is a difference, just an example. You can have a plastic material, nothing happen. If you load, if you apply force, the plastic material start to deform. Removing the force, the deformation remain. Maybe some piece of this one. In the viscous analog, you can put the spherical plastic material that start to deform under gravity force, and deformation is permanent in the same way, but without a limit, a yield strength. Okay. For real rocks to deform, you can see a beautiful shear zone in Canada with a porphyroclast rotated, a very big one. You can see that for the rocks, the deformation is could be represented by this graph with a small part elastic deformation, then a plastic deformation, but not perfectly plastic because this line is not parallel to the to this coordinate axis, but increase a little bit. This means that after reaching the yield stress, you need to apply much more stress to make the rock to flow, to move. Okay, not in the classical perfect plastic deformation. At this point, you have this behavior with the same force, you can maintain the same rate of deformation. In the real rocks, you have to increase stress to allow deformation to go ahead. And this behavior is called also strain hardening. Okay. Instead, if there are some facilities of deformation, easy rocks to deform, such as gypsum or fluid in the rocks, you can have a behavior with a line in this way. So you have to decrease the stress to maintain deformation, and this is called strain softening. Okay? So this just to have an idea of the viscosity of the fluids. Water, honey, basaltic magma, spirited magma, mantle rocks with olivine, and the crustal shear zone. You can see, for example, crustal shear zone has a viscosity uh, Pascal per second, 10 to 15, 10 to 19. So very, very high viscosity of the rocks, comparable or a little bit lesser than mantle rocks, much more than silicate rhyolitic melt, and much more than basaltic magma. Just to have an idea, because we have usually um, information like this. Okay, So we go towards the shear zone a little bit. So shear zone and faults. Shear zone are ductile structure, fault are brittle structure, but they show strain localization. So deformation is localized in a very thin sector of the lithosphere, brittle if you have faults, and ductile if you have shear zone. Shear zone is characterized by continuous ductile deformation. So if you have a displacement of these two blocks with no loss of continuity and no fracturing between. Whereas brittle deformation is discontinuous. You have a fracturing here, loss of cohesion, and you have the same displacement but with much more localized deformation along a fracture of a damaged zone characterized by cataclysite, tectonic breccia, and so on. Whereas in shear zone, the deformation is continuous. Mm. You can see here a brittle deformation uh, deforming these rocks with this dike. Okay. Okay, this graph used by Fossen, you can see here brittle deformation, plasticity as deformation mechanism, and plastic deformation, because the plastic is the terms related to the rheology of the materials, whereas ductile is related to the structure. It's not the same. Right? So you can put brittle, plastic material, non-ductile, and ductile. You can see here the folds, semi-ductile shear zone or brittle ductile transition, and the shear zone, ductile shear zone. Just another way to see the same things. Okay, here an example of geological structure. Do you know what is this? Some of you? Tension gases? Yes. This is a typical brittle ductile transition because you have fracture like this, filled by material, maybe calcite or quartz, but the deformation is not along a plane, but is in a wider part of the rock. Some of you can say the sense of shear. What is the sense of shear in the tension gases? Up to the right, in this way. Yes, yes. And these are fractures that start in this position because more or less you have a sigma 1 like this. So you have the maximum compression, maximum extension, and after moving, the fracture rotate towards the right, and the new fracture forms in the good position with respect to the sigma. So you have this sigmoidal shape. And what is the picture on the right? There's maybe shear zone, but because maybe this is a granite from the Alps where Menegone and Pennacchione studied, good morning, studied a lot of shear zone because there is a very nice place left free by glaciers that are melting and melting. So up to 20, 30 years ago, this area was covered by glaciers. Now it is completely exposed and very, very clean. And you can see this granite undeformed, here undeformed. And you can see here localization of the formation. You can see isotropic rock, and you can start to develop the foliation like this. And then there is an intense development of melanolitic foliation inside the shear zone. So this is a completely ductile deformation. You can assess the sense of shear of this picture, in this picture. Try. Hmm. Top right. It is top right because you can see this foliation going in this position and this in the opposite part. So the movement is like this. Okay. We will go in depth in kinematic indicators in this afternoon. Okay, to try to be sure of the kinematic indicators. Okay, this is just terrorism, but I will not go in in detail of this because of the laws that rheological laws that affect ductile deformation are expressed in this way. This is the velocity of deformation with several kind of terms, exponential law. So these are not single lines, but curves in the diagrams. And this explain the behavior of the rocks, but just uh, so you have not a question like this, but is more or less exponential law is the exponent that could be 2, 3, 4. 2 it's okay, 3 it's okay, but 4 is very complicated. And deformation, just to have an idea, is related to stress, the stress exponent, that is very important. The grain size of the rock is very important, and it is related to stress and strain. The grain size exponent, the temperature, activation energy, and the universal gas constant. So it is a little bit complex, but could explain the ductile behavior in the ductile part of the crust. Just to have, just to recall this. Okay, and the for exponent n1 are viscous materials, so-called Newtonian materials, that is much more easy to deal with. And if n is larger than 1, you have a power low materials. So n could be 2, 3, and are a little bit more difficult to explain. And this kind of law regulates the behavior of the rock in the ductile deformation, where you have plastic flow by diffusion or crystal plasticity. We go into depth of the formation mechanism tomorrow. So to understand the formation mechanism in this part of the lithosphere, we need to look at the crystal lattice of minerals, how the mineral deforms, how rocks deforms, are regulated by deformation mechanism, and we can recognize this deformation mechanism under the microscope. It is quite easy to recognize different kind of deformation due to different lattice deformation of the crystal, but we need not to go at the transmission electron microprobe or electronic microprobe, but just to look at the microstructure of the quartz, of the feldspar, of the calcite, we can infer the formation mechanism in the ductile deformed rock. And we will deal with these things in the next, maybe tomorrow. Okay. Okay. Have you some question about this part? Okay. Crystal plasticity means the formation inside the crystal by the movement of defects in the crystal, maybe point defect, linear defect, or planar defect. And diffusion is the movement of atoms at the surface of the crystal. So a little bit different. We will explain tomorrow. Thank you for the question. Okay. So we can go ahead with the shear zone. Okay, so we go into depth in ductile deformation by deformation in shear zone. I avoid folds and foliation. Foliation we will deal with in the next lesson, but the folds I assume that you are trained on the folds and a little bit lesser on the shear zone. So in this part, we will define what is a shear zone, what is a deformation within a shear zone, evolution of the fabric in a shear zone, different types or kinds of shear zone, and what are myelonites and how we can recognize. Okay, so we are in this part. Deformation characterized by ductile structure. You can see the shape, this shape is due to the power law deformation with the exponent maybe equal to 2 or more or less. And in this kind of crust, you can find ductile, completely ductile shear zone. So ductile shear zone are long and narrow zones of relative displacement. They are the same analogous to fault, but without fracture planes, unless they are reworked, because in nature you can have several superposed deformations. So you can have a shear zone, then fractured, or fractal, then shear zone. So, but a single shear zone usually has no plane of fracture uh, because dominantly ductile deformation has caused the concentration of large strain into the shear zone. So it is a concentration of deformation and shear in a narrow and very long zone. Deformation in the ductile shear zone is associated with a drastic reduction of the grain size and development of well banded and lineated rock called myelonite. Ductile shear zone records non-coaxial deformation. So there is a deformation characterized by both simple shear and pure shear, because the simple shear and pure shear are end members of deformation. But in nature, you can have usually the combination of these two factors in a shear zone. And shear zone may range from the grain scale or microscopic scale to the scale of 100 of or 1,000 of kilometers in length and a few kilometers in width. So the scale is not a problem. In the Himalayas, there are, of course, a very huge shear zone. The main central thrust run all over the Himalayas for 2,000 kilometers. The same as the South Tibetan detachment in the upper part of the Himalayas has 2,000 kilometers in length, and the width maybe up to 1 kilometer. So the main central thrust is up to 4 or 5 kilometers. So the scale, and also the displacement could be few centimeters up to maybe 2,000 kilometers for the main central thrust or other important shear zone. Okay, the localization of the formation in the shear zone reflects the continuous but heterogeneous strain in the rock. So, according to the initial definition of Ramsey-Huber, shear zones are defined as planar or curviplanar zone of a deformation to have a length much greater than their thickness and surrounded by rocks characterized by significant lower deformation. This is a shear zone from the Adamello granitoids in Italy. This is non-deformed. This is a shear zone with a strong deformation, and this is undeformed. And there is also a spatial gradient of deformation. Cioè, in the space, you can observe a gradient, an increasing deformation from this part towards the center of the shear, and then deformation decreases towards this part, towards zero deformation. Is just an example of a granite before deformation. You can see quartz, plagioclase, tight, diciamo, with no deformation, isotropic fabric that could be represented by a circle. And then after deformation, after simple shear, you can see here the circle became elliptic. You can see that the minerals are deformed, are aligned in this position, are stretched in this way, and compressed in this way. So the shear zone causes a deformation of the granite of this granite in a shear zone. Mm. We are in the Variscan shear zone in the island of Corsica. It is politically belonging to France, but once was belonging to Italy to some centuries ago. And you can see the here, wall rock here, and then a big shear zone. But you can see that here there is a foliation. There is an older foliation with respect to a shear zone. So you have a regional foliation acquired during Variscan collision, then a shear zone affecting this Variscan collision with a new deformation concentrated in this part of the shear zone. So in the ideal case, like this, the wall rocks is completely undeformed because you have here only the granite crystallization and the shear zone. But in the mountain belt, you observe usually several kind of deformation superposed. So the regional one, this one, and the shear zone. And you can observe a thickness of the shear zone that more or less half a meter. Uh, Grain size reduction. You can see these are more or less feldspar crystal that are very little bigger here and very small here. The white point in the myelonite. So deformation during the shear is concentrated in this part. And you can see also the older foliation that is folded by the shear zone in this way. Okay. Here we can see in this nice experiment by gypsum. Gypsum is undeformed. You can see the crystal under the microscope. Isotropic crystal with no deformation or so nothing of strain. You applied a shear stress. You can see the shear stress here, gamma, that is the tangent of this angle, the gamma, for the simple shear. And the deformation was at room temperature. You can start to move the upper part to the left, and you can see the gamma is more or less 1, so the angle is 45 degrees. Mm. And just with gamma 1, you can see that this crystal, that are more or less rounded, became stretched and aligned in this direction. And also the color is different. You can see here green, blue, red. In this part, the color of the crystal are the same. That means that the crystallographic orientation is the same. This the crystallographic orientation is in different position. This is concentrated, aligned in one position, and it's very nice. You can see the development of the shell zone until the breaking of the sample, because of course it is a few centimeters, so it is not possible to have a big deformation. But you can see uh, strong localization deformation with strong crystallographic orientation of the minerals. This is gypsum, but the same happens from quartz, calcite, olivine, lawsonite, depend on the metamorphic grade of the shear zone. You can see again, give a look also to the gamma increasing. So means that the angle of shear is increasing, giving to the left sense of shear. Okay, in this graph by Jean-Pierre Bourg, that was professor of structural geology at the ATH in Zurich, Polytechnical Federal Institute of Zurich. Jean-Pierre Bourg is very famous in Himalaya because he discovered the South Tibetan detachment in 1983, because at that time it was considered a trust by Chinese geology, but he studied the leucogranites deformed along the South Tibetan detachment by studying kinematic indicators such as like a mica fish as the structure. He recognized a uh, normal shear zone, normal sense shear zone. It was a very nice discovery because at that time all the people believed that mountain belt are made by compressional tectonics. It means folds and thrust to no shear zone or extensional shear zone or extensional fault. But after 1983, people started to think about both contractional and extensional shear zone at the top of the Orogen, and some models were developed. For example, the John Platt model is compression at the base, extension at the top. So different model start to be involved in the mountain belt. But the starting point was Jean-Pierre Bourg working as a for the PhD thesis in Tibet. Stayed maybe 2 or 3 months in Tibet looking at the deformed rocks. And by recognized kinematic indicators, he gave the right interpretation of this huge shear zone. Okay, so coming back to this graph, you have here deformation, axial deformation. Axial load means stress. You can see the red line, the classical shape of deformation, very general shape, linear, uh, and plastic with strain hardening. But usually you have recoverable deformation up to this point, then homogeneous deformation. Then there is a possible bifurcation of deformation in every stage. You can continue to deform the rocks by homogeneous deformation, or you can localize deformation along shear zone. So the meaning is very general for this. But at any stage of deformation, you can start to localize deformation, maybe for the presence of fluids or crystal oriented in a particular way, allowing deformation to flow in a particular direction. So in this way, you can deform the lithosphere and make a lot of displacement along the shear zone. So, so you need to localize the deformation from homogeneous deformation to localized deformation. Okay, this shear zone from the Jotun Napp in Norway, Caledonites, and you have a shear zone with malonite is enriched in epidot, because there is maybe a decrease in deformation and the presence of fluid, allowing the crystallization of epidot inside the highly deformed area. And you can see all the characteristics of the shear zone: localization, less deformed wall rock below, above, grain size reduction. You can see big crystal, maybe feldspar here, and the small feldspar here. That amount of foliation, fine grained defoliation here, and the extra sense of shear is detected by the defoliation attitude. This is a very good example. This is another example from Pennacchione in Adamello, the same feature. So this foliation is growing during the formation of the shear zone, because no foliation outside, but foliation inside the shear zone. About the scale, is a nice paper, a review paper for the shear zone by Hakun Fossen and Carolina Cavalcante in 2017 in Earth Science Review. This is a nice paper. I suggest you to have in your library. And this is a shear zone at a microscopic scale with displacement more or less less 1 centimeter. And this is a shear zone in the Canadian Creton, Canadian Creton, with displacement of several hundreds kilometers, but the general meaning is the same. So deformation is independent from the scale. Okay, shear zone is made in this way. You have undeformed protolite, This part is displaced to the right. In the shear zone, you can develop a foliation like this. Above the foliation, you can see elongated crystal or minerals or deformed objects. And the foliation became stronger and the shear zone going towards the center of the shear zone. Usually, the best description in mathematical terms is assuming that the rotation axis epsilon is this one, and the epsilon is equal to 1. So this is a condition that is named the plane strain. So you have deformation along the x-axis and the z-axis, shortening, elongation, with no deformation along this axis. Also, the axis of rotation, that is monoclinic flow, because the axis of rotation is oblique. You have a triclinic deformation, but it's very difficult to deal with. But in some papers that we made with Case Pasquier and my former students Jacopini, we found with numerical models that increasing the deformation, you can start by triclinic deformation, but with increasing strain and time, deformation became monoclinic. So in very high strain shear zone, the assumption that rotation axis is this one is almost correct. If the deformation is low, it's a problem, but with a very strong increased deformation, this assumption keep. Another important thing, you have defoliation stretch inclination, marking the x-axis. And this plane is the plane where we can observe the foliation, the shear zone, and the kinematic indicators. It is the XZ plane of the finite strain ellipsoid. You can observe kinematic indicators only in this plane because in other plane you can observe the component of the formation. So you can you can have you can have not the right information about the sense of shear. But it is very important to have the right sense of shear in geographic coordinate because if you put on the map this right sense of shear that is top to the northeast, if you have a cut in this direction, you can have a component to the north, and you can put the wrong sense of shear on the map. Okay? This is just a movie from Fossen. There is a website of the Book of Fossen where you can download this kind of movie pictures. It's very useful. Here you can see the shear plane, the deformed object, projection of lineation on the shear plane, and you can see that the object became much more stretched. Oh, è andata avanti. Okay. The object is much more stretched and rotate towards parallelism to the shear zone. Is shown also in this picture. You can see the shear zone is growing. Displacement to the right. The shear zone start in this small part and then increase in thickness. The deformation is represented by these green ellipses that become more stretched in the central part of the shear zone. In this graph, you can see the gamma, the shear strain that is related to the amount of shear, and the angle theta prime that is in between the x-axis of the strain ellipsoid and the shear zone. And the angle starts at 45 degrees in simple shear, and then decreases a lot, became parallel to the shear zone boundary when the gamma is much more larger than 10. Okay, so the strain ellipsoid became more elliptic, an isotropic shape, and rotate a lot to parallelize to the shear zone boundary. And this is the matrix of the formation in 2 dimensions. Gamma in this position means that the formation is like this. So no displacement along the vertical axis. So it is just to remember that in this kind we speak about heterogeneous shear zone because the shear strain changes along the profile. The shear strain has a amount different from here, 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 and here. So the displacement is calculated by this integral between the thickness of a shear zone in considering the strain, the shear strain, or you can sum the along the profile. So usually the formation is a classical heterogeneous in the shear zone. It is very, very rare to find homogeneous deformation in the shear zone. They change a little bit continuously. I have never seen a homogeneous shear zone in my life. Theoretically, it's possible. In this picture that you can find in the book of Fossen, but also in the review, you can see a small shear zone from Adamello. This is the thickness of a shear zone. And along this profile A, B, and C, you can find a different amount of displacement calculated by integral. So the heterogeneity is not only in this position, but also along the shear zone, just at the small scale shear zone because it is 12 centimeters. In this graph is referred to this picture. You can see the shear zone, the extra shear zone, a dike entering these positions and displaced this way, a dike entering at 90 degrees and displaced by the shear zone. So you can observe different behavior. R is the axial ratio of the strain, finite strain ellipsoid, x over z, this one. And with increasing strain, the axial ratio increase continuously with increasing shear strain. The angle theta prime decreases from 45 up to tend to parallelize the shear zone with increasing the shear strain. But you can give a look to the angle. Beta 2 is this one. Beta 2 means a dike entering the 150 degrees to the shear zone and then rotate to parallelism to the shear zone. The same behavior is from a dike entering at 90 degrees perpendicular, then deformed, transported by the shear zone, and then going outside in this part. Also in this case, the formation tends to parallelize this angle to the shear zone. So the shear zone is an attractor because all the lines tend to parallelize to the shear zone. The only thing that increase it is the axial ratio because increasing with gamma, the axial ratio of the strain increases up to the maximum in the middle part of the shear zone, in the center of the shear zone. Okay, this is a movie showing what I have. In this picture, you can see the progressive simple shear as increment by increment, the deformation increases up to the maximum shear strain and maximum elongation of the object and the rotation of the axis towards the shear plane. In geology, in the field, a gamma like 10 is very high. You can recognize easily the angle of foliation and the shear zone because when you are in the field, more or less this foliation could be up to gamma 6, 8, 10. Then you can see a foliation parallel. And with the compass, you can have the enough sensibility to measure an angle less than 2 degrees or 1 degrees. So after gamma 10, it is very difficult to observe it unless you take a sample, you cut in the laboratory, and you study. Since actually you can detect also angle below 1 or 2 degrees. Okay, I think we can stop. It's 1 o'clock. So, okay, we continue this after lunch. I will show you the fabric development along a shear zone with increasing strain and so on. Okay. Have you some question? It's okay. I am going too fast or too slow? It's okay. Mm. Va bene. Thank you.
For this, we can move the geology department to show the practical, right? Because now the camera setup will be
Uh, okay. I think, maybe
you want to show this screen?
yeah,
Maybe you can show it,
because I don't hear what it is. What Thank you. Okay, good afternoon. Now we continue with a little bit with the shear zone, then we switch on the kinematic indicators, maybe 1 hour, and then we move to the geological department to see some thin section of rocks, some practical exercise. Okay, have you a good lunch? Dal bat, pasta, spaghetti, pizza? Uh, different kind of food, but nice. A little bit spicy, in India. For us, but it's good. Uh, ta-da! You see the picture? Wow. Which is the right one? Ah, okay. Ah, okay. Watch it. Okay, in this picture, you can see the development of the fabric in the shear zone with the kind of rocks. So, in this graph, you have the gamma, the shear strain, but you know very well what is the shear strain now, the angle theta prime, the angle of the x-axis of the strain ellipsoid with respect to the shear zone. So with increasing strain, you can see an increase, the red line, increase of the action ratio of the x became much more elongated and the z became shorter and shorter. So the action ratio increases a lot. Whereas at the same time, this angle decreases up to parallelize to the shear zone boundary. So if we can start with deformation, we can we are now in this point, no deformation, no theta prime 45 degrees, gamma 0. So the fabric of the rock is like this. This is a granite, isotropic deformation, no preferred orientation, no foliation, no lineation. But if we start to deform, we have gamma 1, so the angle is 45 degrees. The axial ratio is around 2, 3, 4. Okay. Okay, and you can see the fabric of the rock start to change. The rock is foliated. These crystals are elongated, shortened and elongated in this direction. There is a defoliation wrapping around this crystal because maybe it should be feldspar, much more stronger than the matrix. In the matrix, you have quartz, biotite. So there is a preferred orientation and a strong foliation in the rock with increasing strain. Gamma is this point. Axial ratio increases, and the fabric is much more pronounced with a very strong elongation of the crystal. When gamma reached the 6 and the axial ratio, boh, avanti per conto suo. Okay, in this situation, the axial ratio is nearly 40, 50. That is very, very high amount. You can see a rock that look like strips. You cannot recognize easily the axial ratio because the elongation is maybe 50 meters and 1 meter in thickness. So it is difficult to recognize the object in the field. You have to see the outcrops in 3 dimensions, and there is a strong foliation, and the rock is quite different to the starting point. Okay, so if you are in a very big shear zone, maybe thick 5 kilometers, and you walk on this rock, you cannot see at first sight that is a shear zone. You cannot to walk towards the wall and to observe the gradient of the formation. And so you become aware to be in a shear zone because to be inside and observe only this part, it is very difficult. So to recognize the original rock, mm, because this rock can derive from granite, from gneiss, from migmatite. So different kind of rocks can form this mylonite. And increasing deformation, if you move in this red point, axial ratio is very, very high, and gamma is around 13. You can have a rock like this. So very, very deformed rocks up to maybe this kind of rocks. Maybe this kind of rocks contain some melts. So the fabric is totally changed. So this is what happens when the formation increase and fault rocks and magnetite rocks develop in a shear zone. So it is very important. For example, when I was the first time inside the main central thrust in Nepal, that was with a thickness of 5 kilometers, I was not aware to be in a shear zone because you have to walk towards the upper part, the greater Himalayan sequence or lesser Himalayan sequence, to observe a decrease in the formation, a strength gradient towards the south and towards the north. In this way, you can be aware of the shared zone and to understand fully the rocks that you are observing. Yeah. Uh, this one. Okay, you can produce this kind of fabric with pure shear, simple shear, or both. So the fabric itself is not indicative just from the picture of the kind of deformation. You have to go inside with some vorticity analysis to detect the amount of pure shear and the simple shear inside. Because the final result is the same if you start from simple shear, pure shear, or combination. Okay. Okay. Now tomorrow we will go into depth to distinguish in between the different shear zone. But now we stop with the shear zone and we start to uh, to describe kinematic indicators. So we will try to recognize them later in this section. Okay. That's the problem. Okay, the main kinematic indicators that we can use in a shear zone are deflection or transposition of pre-existing marker or foliation. We saw before some dikes intruding the shear zone, then displaced. These are beautiful kinematic indicators. Then one of the best is the shear band cleavage, the SC prime cleavage that probably you know. This picture on the background is from a leucogranite deformed in the South Tibetan detachment in southern Tibet in a granite showing S and C fabric that will be described after. Then the oblique foliation, asymmetric porphyroclast, quarter structure, and asymmetric boudinage. They are the best kinematic indicators that we can observe both at the mesoscale and at the microscale. Okay, the SC fabric is very easy to recognize because it is very common at the outcrop scale. So it not necessitate observation under the microscope. So it is um, very easy and very good. Okay, the S fabric, if we give a look to heterogeneous shear zone with undeformed undeformed block and heterogeneous deformation inside, you can see the circle and the strain ellipsoid. The strain ellipsoid mark the trajectory of the foliation. That is the X the epsilon plane of the strain ellipsoid. So the foliation has this shape across the heterogeneous shear zone, this one. And this is the S fabric. That means schistosity from the French word schistosité, studied by structural geology in 1979, Berthet, Chocrun, Guzzo, because they found in a granite in Armorica in France a shear zone cross-cutting Variscan granite. The Variscan granite was undeformed, but inside the shear zone were developed a beautiful S and C structure. And at up to that moment, people believed that exfoliation was linked to a previous tectonic event, S, and the second tectonic event produced the C fabric. And in 1979, it was the first paper demonstrating that S and C were produced simultaneously at the same time inside the shear zone. It was a very important discovery for such a geologist. The first SC structure were observed in ice in maybe 1971, because some people studied sheared moraines, and they found in ice crystals a fabric like SC, but such geologists needed 8 years more to understand this kind of deformation in the rock. So SC fabric is made by S foliation with a sigmoidal shape that mark the XZ plane of finite strain. Sorry, the X epsilon is the section, this is the foliation. And the other plane is the C plane, it is one, straight one, that is parallel to the shear zone boundary. And the SC fabric is replaced at the scale of 1 centimeters, 2 centimeters, and it is a little mm, smaller shear zone with the same geometry. So this kind of shape, this S with this C, indicate a dextral sense of shear because you have elongation direction x and shortening direction z in this position in this geometry. Okay, if you have a sinister sense of shear, this ellipsoid should be completely reversed in this direction. So the orientation of the ellipsoid and of the S plane give an indication of the shear sense. So you can have a steeper orientation here, then the line is leaning to the SC plane, the upper part, and the opposite part in the lower C plane. So this geometry is characteristics and indicate a dextral sense of shear. Okay, this is more or less what I said. Okay, with the evolution of the shear zone, with the increasing shear strain, the strain ellipsoid start at 45 degrees in simple shear, then rotate towards parallelism to the shear zone. So at the end, after a certain amount of time or large gamma strain, the strain ellipsoid is oriented in this way, with direction parallel to shear zone. This means that I am elongating the shear zone, and the structure that accommodate this elongation are the C prime extensional shear band. The C shear band are like this. The C prime are synthetic with the same sense of shear, the same arrows, but inclined at 15, 20 degrees with respect to the shear zone. And these C prime extensional shear zone are less continuous and occupy only few millimeters, centimeters the shear zone, but are indicating the same sense of shear. Okay, this is a classical view of the C prime structure, but there is a nice numerical model by Melanie Flinch, a female Australian geologist modelizing a deformation that found that the C prime shear bands are ephemeral. That means they form continuously during the deformation, but they are created, then disappear continuously all along the history of a shear zone, not only at the end. But the sense of shear is the same. If you would like to observe the movie from the experiment, from medical models, you can go to YouTube channel. Uh, you can also find Melanie Flinch C prime, but also if you use this link, you can reach the movie that is very nice. And this paper has been published on the Journal of Structural Geology 2020. Okay. Okay, these are some pictures from Pasquier and Trau, the book. You can see the SC shear bands, the C prime shear bands, and usually in the light that the C prime shear bands develops at the end, in the inner part of the shear zone, you can observe that during deformation, because the shear plane is an attractor of the plane, the lines, also the S and C try to become parallel with increasing strain. So at the end, you can have SC with the same foliation, the same line, and the C prime develops obliquely to the shear zone boundary. To recognize correctly C and C prime, you have to know the shear zone boundary, because otherwise in the field it is not so evident. This is a small movie by Hakon Fossen that he adopted the interpretation that C prime develops at the end of a shared zone. So S fabric, C fabric that is much more continuous, and C prime that is a little bit discontinuous with small planes in the shear zone. Is another view of the C prime shear zone, and you can see that in a sinistral shear zone, all the objects rotate to the left, but to develop C prime, this part has a counterclockwise rotation, an opposite rotation, just to accommodate this kind of object. Okay. Is a shear zone, Carboniferous granodiorite in the Roses, Spain, close to Barcelona, a very nice place because there is good food, paella, there's the rice with fish, meat, very good, good wine, and also beautiful shared zone. We are sometimes with the students to observe because it is along the seaside with very fresh outcrops, very clean. So what you can recognize is an S fabric, is one. You can see more or less granodiorite. Granodiorite means feldspar, biotite, quartz is S-shape foliation and S and C foliation. This shear zone has been studied by several authors in the 80s, especially from United States, Simpson and so on. So they are very famous. Okay, so according to what I said what is the sense of shear? Dextral? Sinistral? left. Yes, sinister sense of shear. These are beautiful C plane. In this point, we cannot say if it is really a C or C prime because we cannot see the boundary of the shear zone. So to be safe, we call C and S, but if we can observe the boundary of the shear zone, probably this is a C prime. But in the picture, we cannot say because we have no information about the boundary of the shear zone. This is a beautiful outcrop, famous outcrop named oyster shell. Oyster is a fossil, more or less. We are in the Moyne Trust in Scotland because you can observe this white stuff are quartz crystallized along sea structure. So the shape is like an oyster. And at the end of the 18th century, there was a long debate about the contact in between the Lewisian rocks and the Moyne rocks. And some people believed that there was a stratigraphic contact, but mm, L- Lapworth was the first who recognized myelonitic deformation in scene section because he collects scene section along this kind of outcrops, and he found decreasing grain size in the rocks, and is started to suppose a tectonic contact. And that really it is a very beautiful tectonic contacts with myelonites, quartz rich myelonites, and C prime structure that is the so these are not fossils, but quartz vein crystallized along the exfoliation with a curved shape. So we have the C plane like this, the C and the S line, and the sense of shear is top to the right. Ecco, in this case, we don't see the boundary, but we can see one plane and one plane with an angle of more or less 15, 30 degrees. So we can say that they are exactly not the same plane, but two plane with a small angle, indicating the same sense of shear. This is a picture from the book of Fossen that we can download directly from separate file. Also, is a beautiful myelonite in Antarctica with C, maybe C prime, and S fabric is beautiful, very beautiful development of this kind of fabric, and also some rotated porphyroclast like or this one. But the sense of shear is clearly up to the left. Okay. We are in the island of Sardinia. These are Paleozoic rocks, maybe Silurian rocks deformed during the Pariscan orogeny that happened during the lower Carboniferous by collision between Gondwana and Eurasia. What you can see here, some CS structure. Why not? Maybe this one, this, this one is a quartz-rich layer with different fabric. Okay, the S are quite convincing. There's also some see structure, maybe this one, this one, this one. In the field, it is not so easy as in the picture of the book to recognize sense of shear. But with this S fabric and C fabric, we can assess a sinistral, destral, sinistral sense of shear. Okay. And this is part of the huge shear zone that we call the ST East Variscan shear zone that crosscut Sardinia, Corsica, Morse Esterel, Argentera Massif in the Western Alps. So it, with a length of maybe more than 1,000 kilometers. Active. Sorry? Boundary? Ah, no. The problem of this shear zone that the thickness is 10 kilometers. So we are inside. This is a quartzite-rich layer with a different fabric, but it is not the boundary. If we take thin section here, you can see the orientation of quartz, quartz preferred orientation, also some rotated porphyrioclast. So it is a different rocks with same similar deformation. Okay. Okay. You can see here in this thin section something similar to C fabric and S fabric. But is it a real shear band cleavage or compression accumulation cleavage? What is the difference? Difference is this one, because when you have folds or superposed folds, you have several foliations. And in this case, you have an older foliation, this one, deformed, folded, and the new foliation, this one, that is a granulation cleavage. But these cleavage are not related to shear zone, to displacement, but are related to superposed folds, two generation of folds. The F1 folds giving rise to this foliation, and there's a second generation fold giving rise to this generation cleavage. So we are in a context completely different from the shear zone. This is a fabric in a shear zone, also from Sardinia. You can observe the C structure, the S structure, but what is the main difference in between these two pictures? Hmm, okay, so exactly. Exactly. In this case, the angle in between the foliation, the S foliation and the C foliation is from 0 to 90 degrees up to 0. So you have several orientation of the folded foliation. In this case, the angle in between the S foliation and the C foliation is not larger than 45 degrees, and then try to become lesser and lesser. So this is strongly asymmetric. This is mostly symmetric. And in this case, we have folds inside. Here you can have folds, but uh, small scale folds like this, but inside the S fabric. So the shape is totally different, but it's very important to distinguish these two cases, because also in published papers in the last year, so also in this year, some people make confusion between this kind of fabric and this one. And maybe one take this picture, and we can say S, sinistral sense of shear, instead there is superposed foliation by folds. This is a different history of the formation and a different, of course, displacement if there are. So in the book of Pasquier and Trau, you can see, you can find some indicators distinguishing between the two cases. There are several indication, but the best one is the angle between older foliation and shear band cleavage, generally between 45 and 90 degrees in superposed folding. And the angle between older foliation and the shear band cleavage is usually less than 55 degrees in shear zone. And there are also some other things that can help to interpret better the shear zone, or not. Mm. Okay, oblique foliation. Oblique foliation, you can have this kind of kinematic indicators in myelonites because of the single grains, such as quartz, very common. This strained deformed in very long ribbons parallel to the main foliation plane. There are very whitish ribbons in the rock. This is the ribbons that you give a look inside. You can observe recrystallized grains like this that are elongate in the direction of extension and shortened in the direction of shortening of the finite strain ellipsoid. And this grain could develop a grain shape, the preferred orientation, that is a preferred orientation of the boundary of the perimeter of the grain, and also a crystallographic preferred orientation. That means that all the crystallographic axes are oriented more or less in the same direction. I will show you an example. Okay, this is a quartz myelonite. That is a main foliation. These are uh, the stripe reached of quartz, and you can see the quartz crystal are recrystallized, and you can see the shape like this, are oriented in this way, and they develop an oblique foliation with respect to the main foliation in the myelonite. There is obliquity of 45 degrees, 30 degrees, or less, because as its strain increases, the angle became smaller and smaller. And in this case, you can observe a shape preferred orientation because the grains are elongated. But if you put the gypsum plate under the microscope, or you can take measurements of the z-axis, you can see also the orientation of the crystallographic planes. This is another example: myelinitic foliation and oblique foliation. It's quite clear. Okay? And the oblique foliation is, of course, related to the sense of shear, because to have grain elongated in this way, you have a compression like this, extension like this, it means a sinistral sense of shear. This is a scene section from Khumbu, the southern flank of Mount Everest. I took this section several years ago, and there are rotated porphyroclast, but also quartz ribbons like this or like this. And you can observe different obliquity of the quartz crystal here that are more or less at 30, 40 degrees with respect to the main foliation, marked by recrystallized biotite and sillimanite along these planes. In these ribbons, the quartz is almost parallel to the foliation, because in each panel, the formation is more or less independent. This started in this way and was frozen in this position. This deformation started in this way, then rotated and was frozen in this position, and so on. So in different parts of the scene section, you can see the same kinematic indicators, but with different angles with respect to the myelinitic foliation, because it is like a clock. It reaches 0, 1, 2, 12, then start again. So the formation start in this way, the grain rotate, 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 then recrystallize, start with a new position at 45 degrees, then recrystallize again. So this is a continuous process. And when the rock is cooled and the fabric is frozen, you can have a different picture of the amount of deformation in each quartz ribbons. But the sense of shears is always the same, is concordant in the different part of this rock. Okay, other good kinematic indicators are the porphyroclast. That means you have big cluster, maybe 10 times more larger than the matrix. That we can divide in shadow and mantled Porphyrioclast. The shape is the same, the geometry is the same, but with mantled Porphyrioclast, the famous sigma and delta of the Greek alphabet, means that the clast and the matrix and the mantle are made by the same composition. If this is feldspar, the tail is made of feldspar. If you have feldspar and the tails are made of quartz, you speak about a strange shadow. There's a small difference, but the kinematic indication is the same. And the other asymmetric posterior class is a mica fish, a crystal of mica with an S shape. Is a beautiful kinematic indicator, especially in granitic rocks deformed in simple shear on so on. Okay, we can understand what happens. We need to give a look to the stiff inclusion, larger than the matrix, the Porphyrioclast, and the sense of shear. With this sense of shear, the strain ellipsoid is oriented with x-axis in this direction and z in this direction. So if you divide the stiff inclusion in quadrants, 4 quadrants, these one are extensional quadrants where material are extended. These one are the compressional quadrant. Okay, these are quite important because when you have a liquid mineral porphyroclast with sensor shear, try to rotate. If my hands are the shear zone, this porphyroclast, when I move the hands, the porphyroclast try to rotate in the same direction of the shear. If it is a simple shear, all the rotation is in the same direction. If you have non-coaxial deformation, pure shear plus simple shear, you have also opposite rotations. But in simple shear, the rotation is in the same direction. So these rigid minerals try to rotate. While rotate, you protect the matrix from the pressure, and if a fluid present in the strain shadow, some minerals could crystallize, such as quartz. For example, you can see here a crystal of starolite with the strain shadow made of quartz with an asymmetric shape, and of course the quartz try to grow in this direction, and in this direction then is moves parallel, is linear to the metric foliation. So at the end they assume an S shape, and this is the same also for the mantle porphyroclast. In this way, with this kind of shadow, the sense of shear is dextral or right lateral, and in this way the same, because you can have the lower part here, the concave shape here, the straight part here, the concave shape here. So there is an asymmetry of the tails, and these are related to the dextral sense of shear. This is in Morse Massif in southern France, a continuation of the East Variscan shear zone that we found in Sardinia, with the same minerals, the same temperature, pressure, kinematic indicators. So in some cases, also at the outcrop scale, we can observe some asymmetric porphyroclast. But the best are observed at synsection. This is another strange shadow. In synsection, feldspar porphyroclast, mica crystals along the magnetic foliation, and the crystal of quartz that are growing in the shadow of the big porphyroclast. This is not easy to detect the sense of shear because the other part is lacking. So I cannot see exactly. I expect to have another tail in this direction, but in this position, but I don't know. So it's not easy in this picture. Okay. Now we can give a look to the best kinematic indicators that are the sigma and the delta ones, because there are several shape of the mantle porphyrio cluster. There are fish shape when the mantle are completely symmetric, or they are much more complex, but the best one are the sigma and the delta object. The sigma is stair-stepping. If you make a median line passing through the center of the porphyrioclast parallel to the magnetic foliation, these tails doesn't cross the line. We start from the bottom on the right to the upper part on the left in a sinistral sense of shear, like this. The observation surface should be the XZ surface of the myelonite. And in this case, the mantle is very thick, huge amount of material from porphyrioclast to the mantle. In the delta object, the situation is different. You can start from the lower part, then the mantle is very thin, it cross the median line and they reach the upper part, then it moves to the lower part, cross the median line, and move in this direction. And these are connected to the sinistral rotation of the porphyrioclast. In this case, are stair-stepping. There is a difference in altitude with respect to the magnetic foliation, and this is a delta object with a non stair-stepping. So the tails start along the foliation and finish along the foliation, but the rotation is the same. Here we can see a section of myelonitic granite in Bhutan. We are in the Great Himalayan sequence. These are leucogranites more or less deformed 20 million years ago. We had some datation, and you can see big porphyroclast of feldspar with the picture is with parallel nickels polarized, only one polarized, and you can observe one sigma shape porphyroclast, also this one sigma shape. There are also smaller porphyroclasts. That means that the deformation is not uniform in section. Less deformation here and much more deformation here. Maybe protomyelonite and myelonite. So deformation is very heterogeneous also at the centimetric scale. In this case, you can observe sigma shape porphyroclast like this. But the problem is that you have several porphyroclasts close each other. So everyone is not free to rotate and to develop the tails or the mantle, but there is interference between different different porphyroclast. There's collision between porphyroclasts. So we should be you should take care of observe porphyroclasts that are free to rotate and pay attention not only to one porphyroclast but to several porphyroclasts or several other kinematic indicators, because especially when there is a component of pure shear, you can have also rotated porphyroclast in the opposite direction. So only one may be confusing. Two are very, very few. You need to use dozen of porphyroclast. This is a beautiful Norway porphyroclast. This is a porphyroclast. You can see beautiful tails here. Became thicker in this part, then moves in the upper part. This is a sigma type porphyroclast with sense of shear. dextral, sinistral is better sinistral sense of shear because you you put the material in the elongation direction, then it moves parallel to the foliation. And to elongate in this direction, you need shortening like this and elongation like this. That is related to the sinistral sense of movement. This is a big porphyroclast in the Makalu orthognathus in the upper part of Greater Himalayan sequence in Nepal. With my finger, you can see big porphyroclast. What do you think? Delta, sigma? Sigma, okay. And the sense of shear is sinistral. Okay, yes. Sometimes there are a problem because porphyroclasts too close each other, but with increasing strain in the direction of compression, the porphyroclasts tend to be close together. This is a picture from a big shear zone in the crystalline massif of the northwestern Alps in the French side, not far from Turin. We are only 60 kilometers away from France. So this big shear zone is in between and Italy, but in France it is well exposed. And here you can see a beautiful porphyroclast, rounded, is a tail here. There are also some shear band here, some C-plane. So the porphyroclast is of sigma type, and the sense of shear, dextral one. In this case, the foliation is almost vertical in the outcrop, and the dextral sense of shear is recognized all along the shear zone from uh, Sardinia, Mors Massif, Argentera Massif, Agui Rouge Massif, all the massif in the northwestern part of the Alps with the same attitude, vertical foliation, subhorizontal stretch inclination, and dextral sense of shear. It's very, very constant. Okay, this is the other part of the porphyroclast that I showed you before. This composition is different. This quartz, feldspar quartz, so we can speak about a strain shadow. The sigma type. You can see also the tails are very huge in this part, they thinner in this direction. You can see this part is straight, this concave and straight. So this is also an example of dextral sense of shear. This is a dextral porphyroclast. The picture made by Pasquet maybe in Namibia. Is in the book. Is a beautiful delta porphyroclast. You can see the tails coming up, down. Is not maybe stair stepping, but this indicate a rotation, a dextral rotation of the porphyroclast. You can try to draw a median line from here parallel to the foliation, intersect the median line here and here. So it is the dextral one with dextral sense of shear. There is also a nice fold here with a long limb, short limb, and a long limb. The folds are sometimes used as shear sense indicators, but they are not so good because uh, in this case there is an agreement between the fold and the porphyroclast, but sometimes asymmetric folds like this are found also in sinistral shear zone. So the folds are the worst kinematic indicators, and we can use the folds in accordance with other indications such as SC fabric, sigma, delta, porphyroclast. Okay, this is an experiment made by Coyne a German geologist, made with camphor. Camphor is analog material of rock, but can be deformed under the microscope at room temperature. And you can see here the rotation of the porphyroclast, continuous rotation, and the development of these thin delta type tails. Okay. You can see again. Is a good example. Okay, these are in the same rocks I showed you before for quartz ribbons. In these rocks, you have also heterogeneous deformation because here you have a lot of porphyroclast, a small amount of matrix. Here you have a lot of matrix and a few porphyroclast with smaller dimension. So there is heterogeneous deformation. Here you can see two delta type porphyroclast. This one a little bit, some asymmetric folds like these. These are quartz ribbons, the ones that I showed you before. The rock is gneiss with biotite and sillimanite. We are in the Greater Himalayan sequence, the metamorphic part of the Himalayas. Okay, so the sense of shear, what do you think? Extra, okay, extra sense of shear. Perfect. Here we can see some movies from Fossen explain if you look at this line, you can see that these sigma porphyroclasts rotate a little bit. In this case, the delta porphyroclast rotate a lot. This is the main difference in between the sigma and delta, because in the sigma there is more rotation and large amount of crystallization. In the delta porphyroclast, we have a lot of rotation of the porphyroclast and a small amount of recrystallization. In fact, the tails are very thin. There are also some other mechanisms to explain this kind of behavior that you can find in the Pasquier-Trau book that are related to the type of flow. It is a little bit complex because they try to explain by the mechanics of fluids. It's not easy, but there are much more details about these kind of tails. Anyway, these are very useful to detect the sense of shear. Oh, sometimes there are structure named the Rolling structure, like Rolling Stone, the music band. It is different, but you can have delta tails and sigma tails in the same porphyroclast. Why we can find this kind of feature in one single porphyroclast? Because maybe the porphyroclast change the velocity of rotation. Because, for example, when you have a porphyroclast inclined 45 degrees to the shear plane, there is a maximum velocity of rotation. But when a porphyroclast is close to the shear plane, it rotates very slowly. So it depends on the initial orientation of the porphyroclast and also on the aspect ratio, because if a porphyroclast is rounded, it rotates very easily. If a porphyroclast is elongated like this, it rotates and parallelize the shear plane and stay in a stable position. So there are several factors affecting the rotation of porphyroclast. And if you start to rotate slowly, then the rotation increase, you can develop sigma tail and delta tail. So the opposite, if you start with a high velocity and the velocity decreases. So it is common to observe also this kind of feature in the metamorphic rocks. In this case, the rotation is always in the same direction, so the sense of shear is top to the right. so no problem. Okay. Another kind of good kinematic indicators are the snowball garnet that are very common in metamorphic rocks. This is a garnet with a foliation outside and inside the garnet. This means that porphyroclast has rotated 90 degrees. This porphyroclast of garnet have a snowball structure. The foliation is rotated several times, and in this draw you can see the concept. You have you can start the growth of the garnet and the rotation because you are in a condition of simple shear or coaxial deformation. So the garnet growth includes the foliation, rotate, and then the growth increase and the garnet became larger, larger, larger. And at the end, it depends on the amount of rotation. You can have a snowball structure like this, very complex, or in this case, you have a rotation like 90 degrees. So you have this picture like this one. So 90 degrees rotation. If rotation continues, you can rotate 90, 180, and so on, 360. So it is the case of synchronic mineral rotating during its growing. The last kind of porphyroclast, asymmetric porphyroclast, is the mica fish, or fish in general sense, because you can have also kyanite mica, kyanite fish, but the most common are white mica or biotite fish. In this section, you have quartz with an orientation like this, and a sigma shape mica, white mica fish, with tails with recrystallized mica with a smaller size, and the smaller size is also around the big crystal. And the geometry is like this. Is the original mica fish is sigma shape, and the recrystallization of mica fragments or separation by stretching, micro shear zone, similar mechanism. So in this case, crystal like this indicate a distal sense of shear, like this one, but it is important to take in mind that this is an old porphyroclast. The new one are these smaller along the foliation or outside along the boundary of the porphyroclast. Because if you try to give geochronological information about the shearing, maybe by laser ablation to detect potassium, argon ages, you cannot use this porphyroclast, but this one to detect the shearing, the age of the shearing. Because also in literature, some people use this large porphyroclast to detect the sense of shear, and the sense of shear, of course, is okay, but the age of the shearing is not good because this is previous of the shearing. The minerals that grows contemporary to the shearing are the smaller one, this one. So you have to use a laser ablation to detect the position and to date this crystal, this one, this. Got un po' di confusione. Okay. So it is very important because sometimes in the paper you can find ages, numbers, but not all the numbers are related to the right process. So you have to take care of this situation. The shape of the mica fish could be a little bit different depending on the orientation of the original mica with respect to the shear sense. So in the book of Pasquier, you can find the percentage of different kind of mica fish It depends also on the basal uh, cleavage of the mica. If it is parallel to the foliation, is oblique, inclined on the positive direction. But in any case, part of with this group that show a shape in an opposite direction, the group 1, 2, 3, 4, 5 are good for to detect the sense of shear. Okay, so the tails that form during deformation are due to sliding along basal plane, rigid rotation, or boudinage of the tips of the mica and the recrystallization. So there are different mechanisms about this. So you can have also a crystal like this with a small fracture and the shearing. So the shape could be explained in different ways. But in any case, mica fish are very, very good. These are other examples with the basal, mm, um, the basal cleavage is parallel to the foliation. This is a little bit inclined. So the shape is a little bit different, but the sense of shear you can detect is the same. And also you can observe also a little bit oblique orientation of the quartz grains that confirm the sense of shear. Is a Carboniferous granite in Sardinia with beautiful mica fish. This is also the eye of the fish, the tails. And in this case, it is very interesting because you have crystallized mica, recrystallized quartz like this one, and fractured feldspar porphyroclast. This is particularly interesting because quartz became ductile at 300 degrees of temperature. Feldspar is ductile above 550 degrees. So means that this deformation at the first sight is between 300 and 550 degrees. So without other information, we can give a look of the position of this deformation. And in this case, the sense of shear is again a dextral one. And this is belong to the system of dextral shear zone affecting the Variscan basement in Sardinia. There is a big shear zone in the northern part of Sardinia and another dextral one belonging to the East Variscan shear zone, and another one in the middle part of Sardinia, the dextral one also belonging to the same system with the same age, but with a different position. Okay, this is the Ordovician orthogneiss in the northern part of Sardinia, the shear zone, feldspar, biotite. What you can see here, some mica fish, biotite fish, some SC fabric. So these are more or less biotite fish. Is a little bit beautiful respect to the others. So the sense of shear is, c'ho scritto? No, Dex. Good. Dex has sense of shear. Ah, we are not far from here, the Mugu Karnali area in between India and Nepal. We are in the Greater Himalayan sequence. And this is a shear zone inside the metamorphic core that I will show you in the next days. This is in the middle part of the Greater Himalayan sequence, and there are several kinematic indicators, and also this white mica with a quite nice shape, indicating a dextral sense of shear. But in the field is the top to the southwest sense of shear. Is a thrust sense shear zone. Okay, another distinction is between mica fish and foliation fish is mica fish or fish, mineral fish, granite fish, is related to one single mineral deformed in this shape. When you have an aggregation of minerals, an aggregation of foliation, you can speak about foliation fish. There's just a small difference in nomenclature, but the meaning is the same. If you have two or more mica crystal, you can talk about foliation fish or similar. Quarter structure, you remember the quadrants that I showed you before. Sometimes the foliation is wrapping around the posterior cluster and is rotated in this extensional quadrant. The compression like this, so you have an asymmetric fold here and a symmetric fold in the opposite quadrant. These are related to the same sense of shear. And there are also mats that are made by compression in this part of the posterior cluster in the compressional quadrants. You can observe sometimes accumulation of mica or myrmecites in this part. So, okay, this Akunfossen show us how asymmetric fold or quadrant fold are developing. So, okay. ISA, do you know what is ISA? It should be instantaneous stretching axis. I spoke about finite strain up to now, but more correctly, we should speak about instantaneous stretching axis. The deformation that instantaneously happen in each increment of deformation. After an amount of increment, you can speak about finite strain, but more correctly, we can speak about instantaneous stretching axis, instantaneous elongation, and instantaneous compression. These axes are constant. Then after a while, the instantaneous stretching axis rotate and became a finite strain axis. So the finite strain increases, but the instantaneous stretching remain more or less the same. Okay. These are quarter structure. This is a feldspar porphyrioclast, and these are myrmecites with a cauliflower shape here. And they are developed in the compressional quadrants of the porphyrioclast. Not here, but in this direction where is the compression. So in this case, this asymmetry suggests a dextral sense of shear because we are more or less in this situation. In this situation. Maybe. So here you can see in the previous picture, you can see some folds in the extensional quadrant here, and here. So also the folds in extensional quadrant are in agreement with the rotation of the porphyrioclast, and also the myrmecites came from some crystal in the same section. So there are several indications in agreement each other with a sense of shear. Okay, the last one is asymmetric boudinage. When you have a stiff material that became deformed in a matrix, maybe leucogranite in mica schist or dolomite in pellite, you can have a different deformation, and the difference between the shape is the shear bend boudins and domino boudins is that domino boudins are more similar to square because there is a strong competence contrast in between the matrix and the layer. So there is a fracture, a strong fracture with antithetic rotation of the Boudins, like bookshelf. Mm. So in the sinistral center of shear, you can have antithetic rotation, and you have this high angle shear in between these rigid blocks. Okay? With a sinistral sense of shear, sorry, with a destral sense of shear, this is the opposite sense of shear in the small fracture with respect to the destral one. In the case above, you have less difference in rheological contrast in viscosity in between the Boudin and the matrix, and the Boudin are a little bit deformed in a sigmoidal shape, and from one Boudin to another, there is a small shear zone at a small angle with respect to the shear zone boundary, with a sense of shear that is the same, more or less. It is similar to Riedel structure. Do you remember Riedel structure? The R1 at high angle, the R at a small angle. It is exactly the same, but in this case, they are useful as kinematic indicators. You can have some other feature, such as the matrix is deformed, is folded inside the space opened in the Boudins, like in this case. Could be the occurrence of some kink bands or some flanking folds with flanking folds are structure uh, that cannot be explained easily in a normal way, such as the uh, we know a fault. If there are some layers at an angle to the fault, they are you can have in a normal fault some how do you say in English? Forgot the name. Help me. What is the name of the foliation where it become carved, closing, approaching to the fault plane? Trascinamento, ma in italiano. Okay. Have you some? Maybe I try to. Drag. Drag. Okay. Drag. Okay. If you have a fault like this, you can have a normal drag in this part and an opposite drag in this direction. But sometimes in the field, you can observe maybe inverse displacement of object and normal drag. So you can have faults or structure with the drag is opposite with the displacement. And this kind of structure are named flanking faults. And you can find some details in the book of Pasquier. And they usually are explained by non-coaxial deformation. You can have a shear zone, maybe the extra one, with a discontinuity in between the matrix. And with deformation, the discontinuity can rotate up to this position. And in this position, you can have a drag of defoliation that could be opposite to the sense of displacement. There are several kinds of this structure. They're not easy, but can be useful sometimes in the field to detect the sense of shear. Because sometimes one cannot explain the difference in displacement and drag of the foliation. Here we are in the Alps, in the metamorphic nappe, and you can see some stiff layers like this with this kind of boudin. What do you think about this displacement? Is more or less shear band boudins or domino? Here, So if this is the plane of shear, is maybe synthetic, so the sense just to be this one. Okay, is it is another outcrop with limestone and dolomites. The difference in contrast, rheological contrast is very high. So you have domino budens. So you have this shape, and it's not easy. It's maybe movement like this. So if it is antithetic, the sense of shear would be left, up to the left. But of course, it is not enough, one picture like this. You can go around, take sample, observe porphyrio class, because it's better to use several objects. This is from Fossen, um, domino Boudin, and also some asymmetric folds that point to the left sense of shear. Okay, this is a simple picture. You have a stiff layer oblique to the sense of shear, and during the formation, you can develop boudins along a previous structure or weak zone in the layer. You can have domino boudin and the shear-bend boudin also at a macro scale, because you can have rigid grains that can break in this hard grain with domino boudin like this on the right. So yeah, you can have domino fragmented porphyroclast with high angle fracture, static. So this is sinistral, and the general sense of shear is dextral. It's okay. Here's an example from the Cap de Creus shear zone in Spain, the famous shear zone studied by Spanish colleagues. You can observe a feldspar porphyroclast with domino-like fracture, suggesting up to the right sense of shear. In this pitch, in this section, you can have also small synthetic fracture and antithetic fracture, pointing to the same sense of shear. The main problem with this kind of indicators is that if the angle is very high, is okay. If it is very low, it's okay. But when you are 50, 60, you are in between, you cannot decide if you are at a small angle or at a high angle. So you can refer only to the end member. Because if you are in angles like this, you cannot decide if you are in one kind of structure or the other. Okay, these are other example of antithetic fracture in feldspar and plagioclase, and synthetic fracture like this. They give the same indication, and this is good. Okay, so asymmetric fold. Asymmetric fold is the worst kinematic indicator. So this is an asymmetric fold in scene section in Sardinia, metapelite and metasamite. You can see long limb, short limb, long limb. So you can put a sinistral sense of shear. Some people use this one, but there is a simple experiment made by Fossen that you can start with a layer like this in a sinistral sense of shear. You start to develop asymmetric folds like this, but when the layer um, rotate in this direction, you develop asymmetric folds in the opposite sense. So if you look this outcrop, only this outcrop, you can say, okay, destra center shear, but you cannot have information about the general history. And if you started in this way, you can reach this asymmetric long, short, long with a different opposite sense of shear. So only faults are not good to use as kinematic indicators. Another feature of the shear zone is the occurrence of sheet faults. Sheet faults are faults, non-cylindrical faults with the axis of the fault completely rotated towards the direction of the extension of the shear, because the direction of extension is a tractor of the fabric. So to the end, you have an axis that is like this, rotate completely and come back in this direction. And in section perpendicular to the elongation dilation, you have closed folds, I folds, like this. This has meta charts in alpine Corsica, performed during the subduction of the oceanic lithosphere. And you have this closed shape and the elongation lineation in this direction, and also the axis rotate in this way. Okay, in this picture, Fossen explain. Some people use this for their kinematic indicators, but you can see that you can have an antiform here and a form in the part. So in reality, they're not good kinematic indicators. It is very difficult to detect the sense of shear. So it is better not to use this one. Okay, this is the same outcrop, and this is a 3D shape of the sheet fold. You can see the axis going here, and coming out from this part. Is this shape like a mushroom? Is not the interference pattern, but it is due to the rotation of the fold axis during the shearing. In this final picture, you can see an evaluation of the kinematic indicators by Paul Bonds, a structural geology from Tübingen, very famous. And he put an evaluation of the reliability of kinematic indicators on the right. For example, he found reasonable asymmetric faults and very bad bookshelf structure. Depends on, but for example, delta are excellent, sigma are good, shear bands excellent, SC fabric good. You can see an overall view of this one. And in this final picture, you can see a recall of the kinematic indicator, so you can print and take in your uh, in your field work, just to remember the kinematic indicators, the shape, what they are, the geometry, just to have to be more confident in the field. Okay. Now, in sections. Have you some questions about this? All right? Bene. Good. So now we move to the, okay.